We present VIS, a tool for visualizing hypergraphs where edges can connect any number of nodes. VIS is the first technique to display hyperedges with no overlap or crossing. Vertices are represented as rows, time periods flow from left to right, and groups can be shown on the left. We designed the layout for readability. VIS shines with mid-size hypergraphs and it allows detailed analysis. We tested VIS successfully using publication datasets and data from historical documents.
Tableau helps you see the stories in your data. It's designed to help you be smarter, so you can make better decisions faster. With Tableau, you can keep on asking questions in the data until you discover the root cause. Share your analysis securely. Your entire organization can access these interactive dashboards from any browser or mobile device to find their own answers. Tableau. Answer questions at the speed of thought.
Ecosystems are complex and dynamic. To investigate the dynamic nature of ecosystems, we have developed a prototype of a visual analytics system based on empirical dynamic modeling, EDM. EDM is a set of analytical methods rooted in nonlinear state space reconstruction. Integrating EDM with dimensionality reduction, brush-linked visualizations, and visual summarization support understandings of ecosystem dynamics.
When visualizing data in a realistic rendered 3D environment, it is important to represent the data in a readable way. In our work, we investigate how the opacity affects the readability of a 2D shape and determine useful opacity ranges. Therefore, we performed a user study with different overlay configuration like filled, striped, and dotted pattern, their density, and considered the effect of an outline.
When developing a deep learning model, people typically struggle to optimize hyperparameters that affecting the model performance. To relieve the pain of this manual trial process, AutoML has been developed as a solution. However, to maximize the potential of the AutoML, people should identify a good AutoML setting for their task. Hypertendril helps to maximize the potential by visualizing AutoML algorithm behavior and guiding effective hyperparameters.
Billions of biologging records reflect animal behaviors on many temporal spatial scales, yet segmenting the time series on multiple scales is often avoided or impeded. Hence we present our MultiSeg VA platform with its 3 contributions. First, MultiSeg VA contributes tailored visual interactive features for multi-scale segmentation. Second, we show a new visual query language to flexibly configure scale-wise techniques and parameters. This VQL consumes a domain-oriented set of techniques, our third contribution.
We present Strat Graphics, an approach for designing data-agnostic and fully reusable visualization templates. Strat Graphics follows the inverse workflow that common data-driven systems. Rather than starting from data, designers construct visualization structures without relying on a data schema. Data tables are shaped later from the structure of graphics. We demonstrate the power of the approach through a gallery of visualization examples.
Spot SDC is a visualization system that helps researchers understand the resiliency of HPC computation kernels to silent error corruptions. It gives users multiple perspectives of details with different granularity about the impact of SDC on an application's output. It also provides novel insight into how silent error propagates through a program's execution.
We present the first generic design space and library for visual piling. Inspired by physically piling paper documents, visual piling describes an interface for spatial organization of visual artifacts into piles of partially overlapping items. Piling affords interactive grouping, arrangement, previewing, browsing, and aggregation to reduce the complexity and support comparison of large collections of small multiples.
Nowadays, online services are used for all kinds of activities. Strategies to increase the situational awareness of personal data stored by online services are needed. We present Transparency VIS, a visual, interactive web application. It allows common internet users to explore their personal data exports, which can be requested from online services like Facebook, Google, Instagram, or Twitter. Feel free to try it out online.
Attention mechanisms have greatly improved the performance of many language models. Yet with great power comes increased complexity. In this work, we present attention flows, a visualization that let users interpret the language model's decisions and gain insights into the underlying self-attention mechanism. We also support model comparison that helps to fill the gaps between models in different training stages.
We present Lyra 2, a system for designing interactive visualizations by demonstration. To design interactions in Lyra 2, users directly manipulate the visualization canvas. The system interprets demonstrations using heuristics and suggests possible interaction designs. We find that Lyra 2 enables rapid prototyping of an expressive range of interaction designs. We're excited to share this work with you.
Suppose you want to see the overall commit structure of a new project repository. Using Git class tools, GitHub Network, or Git log command, it's quite burdensome to get overview and navigate data. We presented Gitthrough as an interactive visual analytics system for the Git metadata to help users explore and understand the context of development history.
How do you visualize the nanoscale, 1 billionth of a meter, for the public? As part of a Science Center exhibition, we developed an immersive environment that explains nanoconcepts by allowing users to explore nanoproperties. We reflect on how exploration, the confluence of explanatory and exploratory visualization, can be applied to visualization in public spaces.
Transitions are widely used in data videos to build seamless changes between video narrative. As the attention cue, they can not only keep viewers oriented but also express narrative information. After conducting a content analysis on the transitions in the dataset, we provide a comprehensive taxonomy of narrative transitions in data videos.
The ever-evolving landscape of malware detection and evasion creates a constant catch-up contest between the defenders and the adversaries. We created a system which submits and analyzes a malware sample with Cuckoo Sandbox and then animates the battle between the malware and the anti-malware system. The Gotta Evade 'em All system is a useful tool that uses a familiar concept based on Pokemon, allowing the understanding of malware evasive behavior to be more accessible.
Entities and their changing relationships can be modeled more precisely as temporal hypergraphs, but hypergraph models are difficult to explore and refine. By leveraging domain-specific geometric deep learning models and a new multi-level hypergraph visualization, our technique allows for the direct integration of domain knowledge into the machine learning process. The multivariate hypergraph model structure can be analyzed on different abstraction levels. Simultaneously, experts can integrate their domain knowledge on the fly, and then explore the refined machine learning model.
Analyzing urban heat island phenomena, which cause higher temperature in cities, requires to explore the relationships between climate and urban morphology. In an ongoing co-visualization framework, we propose different ways to visually explore both urban and climate data at a city block scale in order to support the analysis of urban heat islands.
This is a picture of a Tableau visualization within the browser. The data behind the visualization does not exist here, and Tableau is not running. This is just an image. However, parts of this image are fully interactive. Please join our presentation to see how we can share interactive visualizations across the web, free from any dependency on data or visualization application.
The transport dynamics in an unsteady flow can be visualized by the finite time lab on of exponent. But what happens if the flow contains random Gaussian deviations? We introduce a recently published quantity that is similar to the FTLE but considers these stochastic deviations. We discuss the application to real-world data, compare it to prior methods, and present a complementary visualization.
With the proliferation of AutoML systems, it's now easier than ever for non-experts to create and deploy end-to-end machine learning pipelines. These systems explore the model search space and optimize hyperparameters in order to solve a particular task. We propose Pipeline Profiler, a tool that enables the exploration and comparison of machine learning pipelines produced by multiple AutoML systems. By analyzing these pipelines, we have the opportunity to better understand how AutoML systems work and obtain insights that can be used to improve them.
We present NL4DV, a toolkit that helps prototype natural language interfaces for data visualizations. NL4DV provides a high-level Python API for interpreting natural language queries. The API automates the core tasks of processing natural language queries to infer relevant information and determine appropriate visualizations, allowing visualization developers to focus more on designing and implementing the user interface.
Data videos are quite popular nowadays. They usually show changes in the data. However, creating a data video requires multiple skills, and the process is usually laborious and iterative. Our approach focuses on automatic and interactive visual enhancement of important changes in time series data with data video.
In this study, we designed a system named Causality Explorer to facilitate the causal analysis. Users can explore the causal graph to perceive the causality and its uncertainty, validate the causality with the raw data, and apply the confirmed causality to what-if analysis.
Asteroids have always been and will always be a threat to life on Earth. Most likely, an asteroid will hit deep water, but what properties will actually lead to a threat like a tsunami? Ensemble simulations are a common tool to understand the effect of different parameters like the size of the asteroid. We propose an interactive visual approach to help analyzing deepwater asteroid impact simulation ensembles.
After determining the departure timestamp, the experts then moved to verify the recommended shuttle stops and routes. Note that VisComm recommends the default shuttle stops and routes based on the metric of average distance. Then they observed that in our cluster 4, the system recommends Yixuan as the shuttle bus stop, but the experts identified that another drop-off spot Panshanhuiyuan is located in the middle part in this regional cluster.
Confusion flow is an interactive visualization for the performance analysis of classification models. It introduces a novel temporal adaptation of the confusion matrix, which lets model developers compare the learning behavior of multiple classifiers over time. Find out more about confusion flow in our talk or in our TVCG paper.
Magazine-style narrative visualizations can be challenging due to the need to go back and forth from the text to the visualization. We use eye tracking to monitor which sentence is currently being read and trigger visual links between that sentence and the corresponding data points in the visualization. Results show that the gaze-driven links increase comprehension of the documents without hindering reading time.
Tableau helps you see the stories in your data. It's designed to help you be smarter, so you can make better decisions faster. Connect to the data you care about. Sort, highlight, drill down, or filter your data in seconds. Add calculations to extend your data. With Tableau, you can keep on asking questions in the data until you discover the root cause. Tableau. Answer questions at the speed of thought.
In this presentation, we introduce a provenance library, Track, which makes implementing provenance in web-based tools.
Hello, and welcome to VisComm 2020. I'm Adriana Arcia. Alvitta, Robert, Ben, and I are delighted to welcome you to the third workshop on visualization for communication, and the first to be held virtually. I recommend opening up a browser tab and heading to viscomm.io. There you can find the agenda, the papers and case studies, and any links you'll need for today. First, we'll do some introductions, and then we'll go over what to expect today and how to participate. As I mentioned before, my name is Adriana Arcia, and I'm an assistant professor at Columbia University School of Nursing. My research is focused on using tailored information visualizations to make it easier for people to understand their personal health information, particularly if they have low health literacy or limited English proficiency. We use hybrid iterative participatory design so that we're taking advantage of expert opinion and best practices while keeping the needs and preferences of the target audience at the center of the design process.
Hi, I'm Robert Kosara. I'm a research scientist at Tableau. I founded this little workshop with Ben Watson a few years ago, and we're doing this for the third time this year. This time, of course, very different from the previous ones, but I'm very glad to see how much interest it has garnered over these few years. My personal interest has been in communication with visualization for a while, whether you call it storytelling, which isn't really a term that I love all that much, never really have, or whether you call it communication or presentation, and certainly also news graphics. Those are all really interesting topics, I think, and we're going to see a really good overview of the different kinds of things people do with them at this workshop. So I'm looking forward to seeing all the papers.
My name is Alvitta, Ottley, and I'm an assistant professor in the Department of Computer Science and Engineering at Washington University in St. Louis. I'm also the director of the Visual Data Analysis group there. And in our group, we do a wide range of research, ranging from understanding how visualizations can aid or even bias the decision-making process, largely in the medical realm. And we also look at how individual differences like personality and cognitive abilities impact the way people use visualization tools. And finally, we apply machine learning techniques to learn in real time what a user is trying to do and who they are, so that we can provide real-time support to a user.
Hi, folks. My name is Benjamin Watson. I'm Associate Professor of Computer Science at North Carolina State University, where I direct the Visual Experience Lab. I co-founded this workshop 2 years ago with Robert Kosara, and it's really been a treat. I've been studying communication with visualization for several years, and I'm really looking forward to seeing all the great work this year.
All right, let's talk about how this is all going to work. As soon as we finish our welcome, we'll go right to the recorded talk from the first speaker, followed by a live Q&A in which your session moderator will read out the questions that you all type in. There are 2 ways you can submit questions, through YouTube and through Discord. If you're using YouTube, the chat box will be next to or below your video. Alternatively, you can follow the link on the website to join the Discord server. You can enter questions and comments there as well. No need to try to do both, though. They will be synchronized. Discord questions will appear in the YouTube chat and vice versa. Type in your questions as soon as you think of them so that we can jump right in at the beginning of the Q&A. The individual Q&As are about 3 minutes each, and towards the end of the first session, we'll have a general 10-minute Q&A related to any of the Session 1 papers. You might notice something of a health theme throughout the session. We'll take a break at about 1:30 Mountain Time, and then go right to the first talk in the second session at 2 p.m. We'll be using all the same links, so feel free to keep the conversation going during the break. But that's not all. On Thursday, we'll be having an informal Zoom meetup. The meetup is an opportunity to network with others interested in using visualization for communication. Come to find a collaborator, discuss best practices, share resources, or just have some social time. It will start at 1:40 p.m. Mountain Time on Thursday to give you a short break after the last conference session of the day. Go to VisComm.io for schedule and details. We hope to see you there. At VisComm.io, you'll also find instructions for joining our mailing list. We'll use it to keep you updated about future workshops. Finally, Ben and Robert have been co-chairs of this workshop for 3 years and are going to hand things over to Alvitta and me. We're looking for new co-chairs to help us organize and take over the workshop in the future. If you're interested in doing that, please talk to us. And with that, let's go right to our first talk.
Okay, All right. Our first speaker today will be Janice Song from the Georgia Institute of Technology. She's presenting a paper on mapping the landscape of COVID-19 crisis visualizations. Janice.
Hello everyone, welcome to this talk, Mapping the Landscape of COVID-19 Crisis Visualizations. This is Janice from Georgia Tech, formerly at Northeastern University. A great number of visualizations have been created to help people make sense of the complexities of the pandemic and understand the evolving public health crisis. Crisis visualizations are being circulated daily. These visualizations have been produced by diverse content creators and disseminated to a large number of audiences. Given this great amount of visualization production consumption, there's an urgent and critical need to document and organize these efforts in a timely manner in order to provide guidance for emerging visualizations. Moreover, it is important to understand what visualizations have been designed and disseminated to the public, because information consumption can impact people's behaviors, attitudes, and thus ultimately the path of the pandemic. This paper reports on our content analysis of COVID-19 visualization collection that we assembled. For the details of the methodology, please refer to our paper. In this presentation, I will be presenting some of our findings. Based on our analysis, our work derived 6 categories of high-level messages, including informing of the severity, forecasting trends and influences, explaining the nature of the crisis, guiding risk mitigation, gauging the impact of the crisis, and communicating risk, vulnerability, and equity. As well as subcategories of the messages. For the sake of time, I'll be focusing on informing of the severity and communicating risk, vulnerability, and equity in this presentation. There are many ways to visualize information to inform of the severity. These approaches mainly include temporal visualization, geospatial visualization, and multivariate visualization. The most basic solution was to visualize daily and cumulative numbers over a time period, mostly using bar charts, line charts, and area charts. For example, this bar chart shows the new reported cases by day in the US from February to early April. Later on, more visualizations started adding moving averages to better reflect the current state of the pandemic. Most visualizations in our corpus that were created early on in the pandemic did not use moving averages. To our knowledge, the New York Times added a 7-day average starting from April 7th, and the earliest use of moving averages was from a report from Singapore on February 29th. But novel visualization techniques were also introduced later on, such as the path charts, the growth charts, and the use of temporal event alignment. The path chart shows the case number changes in horizontally placed blocks, with the x-axis representing time and the color of each block representing the values. When stacking multiple horizontally series together, it is easier to compare trends across multiple regions. In addition to temporal visualizations to depict the trajectory of the pandemic, geospatial visualizations displayed variables of interest over maps to demonstrate which regions were impacted and compare how the impact differs by regions. Among all the map-based visualizations we analyzed, color-plus maps were the most popular option, followed by the proportional symbol maps, especially the bubble maps. Color-plus maps were the most frequently used geospatial visualization in our corpus. They do present a challenge in that color-coding raw data may mislead viewers. For example, if a highly populated state has the same case number as a less populated state, the color will be the same on the map. The reader may interpret a map as conveying that the intensity of cases is similar in the two states, while actually the intensity in the less populated state is higher. While prior work has shown that normalizing data may help remove this sort of bias. Our findings suggest that only 37% of the visualizations in our corpus use some form of normalization. Well, in addition to informing the severity, there are some work that's been done to communicate risk, vulnerability, and equity. One of the most commonly used approach is to impact vulnerability and risk in general, and typically using aggregated scores to communicate risk. An increasing number of visualizations have added disaggregated demographic data in their existing visualizations as governmental authorities begin to release this sort of data of the patients. For example, using bar charts to display demographic distribution of affected populations. However, these factors associated with socioeconomic status are not equally visualized. Age distribution was the most commonly visualized, followed by the race and gender. Our findings show that the number of visualizations created by a variety of information outlets help communicate risks and unpack issues around vulnerability and equity amidst the COVID-19 pandemic. It is important to communicate that some populations face greater risks than others because it highlights inequities that exist within society and calls attention to areas in which efforts are needed to close gaps in terms of how different communities are impacted by a crisis. However, when visualizing risk, vulnerability, and equity, one caveat is that more efforts are also needed to be made to prevent and counteract stigmatization that can arise by focusing on how the pandemic is negatively impacting a group. So far, we have described some visualization techniques and visual encodings to communicate some type of the messages. To move forward, we suggest a couple of directions in terms of how future work can build upon our work to further explore the space of the crisis visualization. First, we call for evaluation of existing COVID-19 crisis visualizations for each type of messages to examine what are less effective and more effective to visualize and to what end. Second, the great diversity in a number of visualizations in our corpus reflect an increasing public interest in visualization. Yet, this amount of visualizations has also led to issues such as varied quality among the visualizations reflected in our corpus. Instead of advocating for a single yes or no response to the question of whether or not we should encourage more crisis visualizations. We might need to think about, for example, how we can design more effective crisis visualizations through collaborations between experts in design, public health, and crisis informatics research. Moreover, building upon our work, future work can compile a list of visual components, encodings, and visualization techniques that are specifically related to the crisis context. Such glossaries and visualization cheat sheets might be helpful for people who typically are under time pressure during crisis to create crisis visualizations more effectively and efficiently. And I would like to thank and acknowledge many people who have supported this work along the way in different ways. This presentation only covers a very small proportion of the content in terms of what forms of visualizations have been used to communicate what type of messages and the issues of existing visualizations. So please refer to our paper for more details. And we hope our work can spark the conversations surrounding the design and evaluation of crisis visualizations in the future. Thank you so much for listening for this talk. I hope everything can get back to normal soon, and I hope to see you in person somewhere in the future.
Okay, thank you, Janice. I think we have time for a few questions. Let me bring a question out of Discord from Gurka, who asks, I wonder if you've looked at how visualization designers balance privacy, things like age, gender, geolocation, with the need to highlight distinct characteristics of the epidemic spread. Did earlier visualization show more aggregate data, for example?
Hello, my name is Star Liu.
Looks like you need to unmute yourself, Janice.
Oh yeah, I forgot to do that.
Okay.
So the question is that if I look into the visualization designers and how to balance the privacy. So I think the question is about like what type of data and what data the designers get, right? It's not sometimes not really the designer's decision to either aggregate or disaggregated data. Well, they do have the options, but a lot of times, maybe at the beginning of the pandemic, some of the designers, when they get that sort of data, not every single data set has disaggregated the data source. That's why we have seen like other data sources coming up. For example, the very first at beginning of the pandemic, and we all know that Johns Hopkins, they don't really have the county level or more detailed data. And then later on, there are many other data sources like the New York Times and other agencies. They started looking at the more detailed data, and from that, there's more opportunities to either visualize or not visualize in terms of breaking down by age, gender, and race and geolocation. And of course, in terms of the risk of balancing the privacy, I would say, well, I assume like if we don't disaggregate data, we have less risks in theory, and to show the more to risk this part of the population, so people don't have to worry about their personal information will be released or get exposed to the general public. But I think it's a really good question, and I think especially these days, and we are basically in the loss of the information in, and we do have the risks to get our impersonal data to the world in general. But I think it's really, really important considerations when taking into the design approaches.
Thanks, Janice. Remco asks, he says, I'm a little confused by your question at the end. Are you suggesting that we shouldn't have crisis visualization? Or if so, can you explain your thoughts a little bit more?
Sure. Sorry about confusion. I guess I'm not really saying, okay, we shouldn't really have crisis visualization coming up. But I think it's back to the original question, whether or not we should encourage more visualizations, and especially in this pandemic where misinformation and potentially visual information can really impact people's behavior and decisions. When I'm saying that, maybe we can think about really great ways to leverage the experience among different experts. Like usually, based on my limited understanding and experience about talking about with different experts in public health and crisis informatics research, also the visualization designers or practitioners, I feel like each of this party, they really want to be engaged or at least contribute their own knowledge. But the problem is that we don't really have the chances, especially at the beginning of the pandemic, to really kind of first to evaluate the current existing methods and also to evaluate with our general audience. So I think it's not, I'm suggesting not having more crisis visualizations, but because, well, I think you can definitely see that with all the some of the great visualizations, we have seen opportunities in novel visualization techniques coming up. So if we don't just ended up not creating any visualization, so what might be other alternatives? So that's I hope that I answered your question.
All right, thanks, Janice. Thanks everybody for your questions. Our next speaker is Star Liu, and Star is from Emory University, and he's speaking he's presenting a visual case study, COVID-19 Health Equity Dashboard, Addressing Vulnerable Populations. Ready when you are, Star.
My name is Star Liu. I'm from Emory University. I'm proud to represent our team, Dr. Emily Wall, Dr. Shivani Patel, and Dr. Yubin Park, to present a case study on COVID-19 Health Equity Dashboard, Addressing Vulnerable Populations. First, I'd like to acknowledge that our work was supported with funding from the Robert Wood Johnson Foundation and Emory University's Woodruff Health Sciences Center. Development was also supported by the Georgia Center for Diabetes Translation Research. For our agenda, I'll give you a quick introduction to the timeline leading up to our project. Then I'll discuss a little bit about health equity and how that focus has distinguished us from other tools and dashboards. Then I'll present a live demonstration of the interface, showcasing design consideration and actionable data for decision makers. Then I'll conclude with some of our other ongoing work and next steps. As most of you already know, COVID-19 has evolved into a worldwide pandemic, and in the US, it started in January. In the weeks that followed, studies and reports like that of the MMWR from the CDC has indicated that COVID-19 has hit certain communities much harder than the others. So we were motivated to understand this underlying health disparity and social characteristics that's leading to differential impacts, and how those vulnerabilities then could inform localized responses. Now you may ask, what is health equity? Well, health equity revolves around the principle that everyone have the same fair and just opportunity to be as healthy as possible. So it becomes crucial to understand the granular scale risk at each county and each community in order to have the best possible targeted action. As you can see from the heat map pulled straight from our dashboard, showcasing the average daily cases on a county level basis, it really has a differential impact from county to county, from community to community. Now, as we move on to the live demonstration, we'll focus on the interactive interface and the actionable data presented for decision makers. Right off the bat, you're looking at a heat map showcasing the county level data for the entire nation. In this case, it's showing the average daily cases. Now on the right, you're also shown the number of daily cases and daily deaths for each state, as well as a snapshot of the health equity focus that we have, showcasing cases by race per 100,000. And as you hover over each state, you get to see the particular cases per capita and health disparity within your state. Now, in this case, for Georgia, you can tell that the African American population has been particularly harder hit, almost twice as that of the Asian population and 1.5 times that of the white population. Now, this allows you to quickly compare cross-state for the entire nation. And as you click into a state, it'll take you to the state page, where you get immediate access to daily cases, daily deaths, percent occupied beds, percent tested positive, and again, distribution of cases per 100,000 by race and ethnicity. Now, this is incorporating feedbacks from researchers, epidemiologists, and clinicians in order to ensure that the most relevant and important metrics are presented for decision makers to look at. Down at the bottom, again, you have a heat map showcasing comparing counties across a state. And the trend line here allows you to benchmark and compare county level trend over time to the state and nation level. So in this particular example, Pulaski County had seen a huge increase starting August and onto September. And this also gives you a quick snapshot of the Pulaski County population characteristic shown through a bar chart. This gives you some kind of contextualization into understanding the makeup of your population. Now, if you want to understand and take a deeper look at the particular county, all you have to do is click into Pulaski County. And it'll take you to a detailed county report, where again, you'll be presented right up front the most important and relevant metrics. And in this particular example, it would be alarming to see that Pulaski County has a case fatality ratio that's almost 5% higher than the rest of Georgia. Now, this goes hand in hand with the line trend graph shown here, where you can again benchmark county trend to the state and nation. Now, to take a step further, you may look at the county characteristics. And several things that stand out could be connected to the rise in cases and case fatality ratio, or percent diabetes, percent poverty, and percent in good quarters. And if you take a further look at the county characteristic versus outcome relationship through scatter plots, in this one in particular, socioeconomic vulnerability, which ties back to percent poverty, you can see that in Pulaski County really does lie in the higher spectrum of total COVID-19 deaths. So this allows you to take a deeper understanding of the trends in a particular county, compared and benchmarked against the rest of the state and nation. Now, this next feature that we have is National Report. This gives you a systematic overview of how the United States are doing as a whole. So whether it be looking at trends in cases over time, deaths over time, or if you want to understand which cases are making up approximately 50% of new cases in the United States, and as well as some of the top counties and trajectory of those counties with the most cases and deaths. And of course, we also have cases and deaths by county characteristics, which ties back again to the health equity focus. Now, this next feature that we have gives you a quick snapshot of how certain outcome measures are related to certain population characteristics. So for example, in Georgia, you can see that most cases tend to happen around areas where the population is the most dense. So this gives you a quick understanding of the outcome and the factors that could be correlated to the outcome. Now, of course, we also have content update through videos and podcasts, etc., from experts in the field on centering around topics on health equity. Now, the other ongoing work that we have is our collaboration with the Georgia Department of Public Health. We're working on a standalone platform just like ours to take a deeper look at Georgia specifically. And then we're also working on visualization coupled with descriptive narratives using natural language processing, as well as a model projection for COVID-19. Here are our most important takeaways, and thank you so much for your time.
Okay, thank you, Star. Thank you, Star. We have time for one quick question. And then Star, seeing nothing yet on Discord, we may get some for you later. I just wanted to ask a quick question of my own, and that is how, if you could improve it, what would you do better next time, your dashboard?
Actually, I was going to say, the current dashboard that if you go on the website right now, you may not see exactly what was presented. Very much because it's an iterative process. So we're constantly getting feedbacks from epidemiologists on what to show and how to design the space and the interface. So and also choosing different metrics. And at this point, for the front page or for the national report, we're actually going to be presenting mortality rates rather than cases, given that there's a lot of missing data. And so we felt like it wasn't the best approach to show the number of cases, just because there's a lot of missing by race and ethnicity. So that's just one of the examples, right? Like we're constantly making changes in terms of not just design, but then also what are some of the ways to improve the contextualization or understanding of the data. So one thing that we will be doing is actually implementing natural language generation. So the idea that you could immediately get quick access to data facts related to certain statistics. So whether the cases have been rising over the past 2 weeks, or the cases have been going down, et cetera. So we're constantly finding ways to make it better, and we definitely welcome a lot of feedbacks.
Okay, thank you, Star.
Sure.
Right. Our next speaker is Darius from Stony Brook University, who will present a paper on eating with a conscience toward a visual and contextual nutrition facts label. Darius.
Hello everyone, I am Darius Coelho, and I will be presenting our work on designing a visual and contextual nutrition facts label. This work was conducted by myself, two talented high school students, Helen and Maxim Baduk, and my advisor, Klaus Mueller. So let's start off by taking a look at the current nutrition label design. This is an example of a nutrition label design as specified by the US Food and Drug Administration, or FDA. It is a textual label that uses font styling such as font size and making text bold to emphasize important nutritional content of a food product. However, recent studies show that it is still difficult for a large number of consumers to understand and make comparisons between food products. They often make errors when computing and estimating the contribution of food's nutritional content to their daily nutrient requirement. They also find it difficult to compare food products with this label. We attempt to overcome some of these limitations by designing a nutritional label that makes use of a visual representation to communicate nutritional information. Specifically, we aim to clearly communicate the level or quantity of a nutrient in a food product, as well as indicate where this quantity is placed within the range of quantities of this nutrient in similar products. For example, when considering the amount of sugar in drinks on a scale of water to Coca-Cola, we would place juice closer to Coca-Cola. Thus, our visual label must be designed to show exact values of nutrients within a reference range. It should be compact enough to fit onto food products, and should have some level of similarity to the current design so as to fit into FDA regulations, as well as minimize the learning curve for viewers. To accomplish this, we base our design on the bullet chart developed by Stephen Few, shown here. It has a small footprint and is based on bar charts. It also has some resemblance to progress bars, which we believe would make it easily understandable to the general public. I will explain our modified design with an example. Consider we are looking at the product spinach and feta chicken and turkey sausage. According to the FDA's database, it falls under the sausage category, which in turn is in the sausage and luncheon meat food group. We represent each nutrient with a single modified bullet chart, such as this. Here we show the protein content of the sausage. The extent of the entire range is the required daily value for an average adult on the 2000 calorie diet. The light blue bar represents the range of protein content across items in the sausage and luncheon meat food group. Similarly, the darker blue bar represents the range of protein content across items in the sausage category. And the level of protein in the current food, spinach and feta chicken and turkey sausage, is shown with a black marker. We also report the level of the nutrient in terms of the percentage of daily requirement. In this case, it fulfills 30.6% of the daily requirement. Now, with this design, we can easily see that the food contains 15.3 grams of protein, which fulfills 30.6% of the daily required value. We can also see that this food is close to the middle of the protein range of foods in the sausage category or in the sausages and luncheon meat group. With this information, the viewer now knows that he or she can opt for an alternative but similar food if their protein requirement is higher or lower. If a range of value goes beyond the daily requirement, we indicate this by adding an arrowhead to the end of the range. It should be noted that we also follow the FDA font and unit guidelines when labeling the bullet graph. Foods contain multiple nutrients, each of which we represent with a bullet graph. However, there is a limited amount of real estate on food packages. Thus, we consider two layouts. First is a linear layout, where the bullet charts are laid out sequentially from top to bottom and follow the sequence specified by the FDA. The second is a radial layout that arranges the bullet charts in a clockwise manner following the sequence specified by the FDA. The linear layout bears close similarity to the standard label in terms of design. It is essentially the same label, with an additional column in the middle containing the modified bullet charts. The design of the radial layout, on the other hand, deviates significantly from that of the standard label. However, we chose to include this layout as it has the ability to save space as the number of nutrients increase. But we do believe that it will be harder to read. In addition to considering two layouts, we consider two unit encodings. The first is a standard continuous encoding, where the range of the nutrient values is represented as a continuous bar, while the second is a discrete encoding, where each bar is divided into 10 individual segments, each representing 10% of the range. We expect that the discrete encoding will help users to easily approximate the quantity of a nutrient and compare values. Having designed different visual labels, we conducted two pilot studies to test which layout users prefer and which unit encoding is more effective. We start with a layout preference. We tested both the linear and radial layout. We added additional variation of each that primarily differed in label positioning and coloring, and we add the standard label to the test. For the study, we recruited 20 participants who were students on our campus. Each participant received a brief explanation of the labels, after which they were asked to rank them based on which they prefer to use when reading nutritional content or foods. It should be noted that we used grayscale versions of the labels so as to avoid engaging users with the color. We used the rankings generated by the participants and computed a rank score for each label. Higher rank scores indicate higher preference. Here we found that participants preferred the linear designs over the standard design. However, the radial designs were the least preferred. This is in line with previous studies that show that radial layouts are generally not preferred. Next, we tested the unit encoding performance. We test a linear layout with the continuous encoding, a linear layout with the discrete encoding, and a standard label. For this study, we recruited 15 participants via social media. Each participant only used one of the three label types to answer 13 questions about a food label. These questions tested the user's ability to read values and ranges and compare values and ranges. Each participant evaluated two randomly selected food products. The results showed that when it comes to reading values, the visual labels perform significantly better than the standard label. However, the difference between the two encoding types was marginal. But when comparing values, the continuous encoding performed significantly better than the discrete encoding, and both outperformed the standard label. When reading ranges again, the difference between the two encoding types was marginal. This was also the case when comparing ranges. To summarize, we designed variations of a visual food label based on the bullet chart. We conducted pilot studies that showed users preferred our linear layout visual label. However, there were no significant differences between the two types of unit encodings. While our studies demonstrate the potential of visual food labels, further testing on a large diverse set of participants is required. Thank you.
Thank you, Darius. I assume it'll be a minute live. Okay, thank you, Darius. That was a cool presentation and a cool paper. There's some discussion in the chat about the relative merits of the radial and the linear layout. A lot of people found the radial layout visually appealing, but apparently it wasn't preferred or as understandable in your work. And so we're wondering if you got, in addition to these preferences, some notion of what the reasons anybody was expressing for these preferences. They're just samples, I understand, but.
Yeah, I think students just preferred the linear layout. It was mostly visual. We didn't ask them to really read anything as such of the label. We just told them how it works, actually how each label works, and asked them which one would they like to use when they're at a store, if they're in a store. So I think, I don't know why they preferred the linear layout exactly. We have to do further studies, but
okay.
I would say that when you're comparing values, you have to keep rotating a label or a food product, and you may not want to do it or rotate your head. It's just easier to hold two products side by side, and it's linear. The linear layout is easier to compare them, I would say. Yeah, I could totally see people like rotating cereal boxes in the grocery aisle. That would be funny. Have you been able to do any further experimental evaluation or any evaluation work since you wrote that? Not yet, but we've been discussing with nutritionists actually how to go about it, because we'd have to test a wide range of people, some of them who are not very well educated, and they tell us that some of them don't even know how to tell their own age. So we have to go to these clinics and actually test labels. So we're still formulating a way about how to do this, actually. All right. Thank you so much, Darius. I enjoyed it. Thanks. All right. So our next speaker is Dr. Natalie Benda, who works at the Weill Cornell Medical College, and she'll be presenting. Bear with me. I lost it. Making numbers meaningful. That's right. Here we go. Making numbers meaningful, improving how we communicate numbers to patients and the public. All right, thanks. Looking forward to it, Natalie.
Hi, everyone. Thanks for listening in today. My name is Nat Benda, and I'm here to talk to you about a project called Making Numbers Meaningful that is funded by the National Library of Medicine. And as you can see in this graphic that I've included in the corner, given the COVID-19 pandemic and all of the numbers that we see in healthcare, the way we visualize these numbers has become much more important. And the goal of the work that I'll be talking about today is looking at numbers like the ones that you see here, as well as other places in healthcare, about a tool that we're developing to help designers like yourself communicate these numbers in a way that patients can understand. Before I talk more about the project, though, and what we're doing, I would like to motivate why we're doing it. So, as many of you know, numbers are pervasive in healthcare. It's hard to read a news article or go to the doctor's office without being exposed to a myriad of different numbers. However, people in the United States and across the world, as shown by this national survey, aren't always good at interpreting numbers. So as you can see here, a concept that we know well, such as literacy, in this nationwide survey, a lot more people had issues related to numeracy, about 10% more, or interpreting numbers. And furthermore, almost a third of the population fell into this lowest level of being able to interpret numbers, which involved doing, simple one-step calculations in context, which is a bit concerning. And to make matters worse, unfortunately, there's also a lot of disparities related to being able to interpret numbers. So in the first graphic that you can see, for example, those who had fair to poor health, who probably are the ones that experience the most numbers and really need to be able to utilize them, had the worst time being able to use and interpret numbers. And then furthermore, unfortunately, by race and ethnicity, due to other issues about education inequity and systematic racism, those that were Black and Hispanic in this particular survey were shown to have a much more difficult time interpreting numbers, with almost half of the people in those groups falling into this lowest level of being able to interpret numbers. So a lot of this is bad news, but the good news is that we can reduce some of these inequities and understanding by simply changing the design of how we communicate numbers. So as you can see here, using this 1 in 384 versus 1 in 112, that was not as well interpreted as using the same common denominator of 1,000. So we saw a nice increase when we switched the way that the numbers were being presented. And as you can see, although 45% comprehension among those with less than 9 years of education, we want to do better than that. But just changing that simple presentation aspect, people were much better able to interpret the numbers that were given here. And then the last reason that we're doing this is, like there is for literacy from the Clear Communication Index from the CDC or from AHRQ, there isn't an equivalent tool that helps designers best communicate numbers to patients like it does for words. So that's what we're hoping to create with our work. So for the Making Numbers Meaningful project, we are trying to design a tool for health professionals who want to educate people about their health using numbers. And how are we doing that? So first, we're creating a systematic literature review, and what we want to do is use that to develop concrete guidance that we've developed some of it so far, and put that in the form of a website so that people can go there with a specific or non-specific question and get some targeted feedback about the best way to present the numbers that they're dealing with. So thus far in our systematic literature review, we've included 376 papers that are allowing us to help people determine how to best communicate numbers that they're working with. As you'll note here, there was also a project related to medication instructions. We're still working on that, but we've realized that it's really different than communicating probabilities like risks and benefits or quantities like lab values. And so it's just a separate project that I'm not going to be presenting about today. So as I also mentioned, we had to organize this literature in some fashion because there's a lot of differences and a lot of complex relationships. And what we really want to be able to do is to give concrete guidance to say one presentation format is potentially better than another for a given goal of your communication. So we have sectioned off the literature by different quantitative concepts, and then importantly, also by the goal of communication, such as persuasion, informing, and helping people make a decision. And then lastly, we've also been paying attention to if there are certain data presentation formats that work better or worse for people that have lower education, low literacy, or low numeracy, so that we can ensure that we're not creating further disparities with the way that we communicate numbers. So as you can see, using this categorization scheme, we're able to come up with guidance like you see at the bottom of this page. If you're thinking that you have a single value that you want to communicate to make people less worried, as we see here, if you use the X and N or 20 and 100 or percentages, there's some good evidence that people will be less worried as opposed to using this 1 in X or 1 in 5 number to communicate how many people have been infected with COVID-19 in the New York City area. So next, I actually want to show you how a very early version of this website works. And we're going to keep in mind the example that we see from this graphic earlier about what is the guidance for communicating the incidence of hospitalization due to COVID-19. So now you're looking at a very early stage prototype of our website. So this is still under development, so bear with me. But as you can see, you can filter the guidance that you'll be seeing, and then you can see recommendations down here that pertain to whatever use case that you're looking at. So thinking about that COVID-19 hospitalization number, we can first think about what is our goal of communication. So now we'll assume that we want to maybe persuade our audience, and specifically that we want to, just for the sake of demonstration, persuade the audience to take or avoid an action, possibly to continue adhering to good social distancing practices. And then we can also say a little bit more about our number. So this is actually a probability, the incidence rate of hospitalization, and then it's specifically, just for this example, a single probability that we're working with. And then here you can see, you can also display guidance for some of the disadvantaged populations that we talked about. And then you'll get a number of different pieces of evidence. So we can look and see what we have. And it'll also rate how strong the evidence was from the literature that we saw. So here, as you can see, it's demonstrating that there's strong evidence that the way that things are framed change how much people want to take a specific behavior. So for example, if we're talking about hospitalization, people will be more likely to adhere to a specific behavior if we frame something that's going to happen positively. So this percentage of people were hospitalized, as opposed to if we talk about the percentage that were not hospitalized. So another thing that we may be interested in is other ways that we can influence behavior. So there is also a moderate amount of evidence that using an anecdote or a story can influence people's ability to want to address a risk, for example. And then another thing, I know that we all do visual communication, so people may be curious about using graphics. So there's not as much evidence to suggest this, but they do demonstrate that if you want to use an icon array with a few different people in it, that it's better if the icon array has those icons grouped together as opposed to distributed randomly. We can look at even more recommendations. So talking about graphics again, you can also think about what kind of graphics could be used to improve behavioral intention or people wanting to do a specific behavior. And there's not a lot of evidence about this, but there was one study that showed that icon arrays could be helpful in persuading people to take a certain action. So going back to this presentation that we saw earlier, we can use some of the guidance that we got to evaluate what we're using to communicate numbers. And we can see that this particular group did a good job related to the guidance we saw. So they positively framed the information, talking about the rate of people that were hospitalized as opposed to those who weren't hospitalized. They used something similar to an icon array or some visualization to demonstrate this information. Potentially a step further, or another opportunity from the guidance that we saw, would be to include an anecdote or a short story about a patient who possibly was hospitalized due to COVID-19 to help even persuade people beyond the numbers to practice some of the behaviors that we may want them to take. So this has just been a case demonstration of what this website or tool could be used to provide guidance about visualizing numbers. There are a lot of other applications it could be used for, but this COVID case seemed particularly relevant to all of us right now. That said, I'm very excited to have the chance to speak with you today, and I would really like to hear your feedback on how this project is going and take any questions you may have at this time.
Hi, Natalie.
Hi, how's it going?
Thanks, Natalie. One question that we have is, we're wondering if you could tell us a little bit about how you built your ontology that you presented in the middle of your paper.
So it was actually based on the classification scheme that I showed in one of the earlier slides, where we let the literature that we had kind of drive the building of the ontology. And if people are familiar with doing a systematic literature review, you have to pick what elements you're going to extract from a paper. And essentially we use the elements that we needed to extract from the paper to make comparisons, and then also develop a more systematic means for calling different graphics different things. So for example, in our literature review, people refer to an icon array as about 50 different things. So we really use the literature and a few previous frameworks to try and develop that ontology, working with one of our computer scientists, although that's not exactly my area of expertise.
Thank you. I was wondering if how live your site is so far. Are people going there and getting lost or finding success or?
So the site that we currently have that was showing at the bottom of the presentation, that is just telling about the project a little bit more. We're hoping to have a prototype and beta version for people to walk through and look at in 2021. So anyone who may be interested in either participating in a user test or taking a look at that, please feel free to get in touch with me, because we're going to have more user testing going on, and then hopefully eventually a beta version so people can actually interact with the guidance that we have.
All right. Thank you so much, Natalie.
Thank you.
All right. Our next paper, it's actually a visual case study, will be presented by Li Wanying Yang. And the case study is titled Customized Visualizations for Audience-Oriented Communication in a COVID-19 Tracking Story. Li Wanying.
Hello, I'm Liu Huaying Yang, a data visualization designer from Chinese media group of Singapore Press Holdings. Today, I'm going to talk about our work communicating the COVID-19 situation in Singapore to our audience as the situation changed over several months. In Singapore, the first imported COVID case was confirmed on January 23rd, while the first local case was reported on February 4th. We built and launched an interactive web page called Dynamic Tracking of COVID-19 in Singapore to visualize the daily situation reports released by the Ministry of Health. With the audience interest changing, we built multiple customized visualization to help better picture and communicate the situation. In the initial stage, daily new cases remained low, around 10. Instead of overview trend, typically represented by a line chart, local audience were more interested in the details of each case. Based on official reports, we built a journey timeline, where the audience can click to explain the journey and read more information and related news. In this visualization, we show the individual cases with the key dates such as confirmed date, quarantine date, and their residential and journey status, and how cases in a cluster are interrelated, such as traveling or attending events together. In this example, case 42 reported onset of symptoms on February 1st and visited clinics and hospital multiple times before being confirmed. As the number of discharge cases increased, the audience became more interested in the length and the place of hospital stays. We built a two-side bar chart to visualize for each case the number of days between the onset of symptoms and being confirmed, and the length of stays in hospital after. It also allows the audience to sort by case ID or the number of days, group by the gender, hospital, country of origin or age group, and filter by a particular cluster or group. This visualization can help answering questions like how cases are disseminated to hospitals, whether cases of a certain age group are more vulnerable, or whether some hospitals can handle better extra. This is an example of applying filtering and grouping. To fit different devices, we position the data vertically on mobile and made a spiral shape to fit more data on desktop. With the number of new cases crossing 500 per day due to massive screening at the industrial dormitories, the government stopped giving details of cases. We built a new visualization showing a summary. A green bar chart on the top is the distribution of hospitalization days. The red bar chart on the left is the distribution of days of symptoms before being confirmed. A square marker on the axis indicates the median days. The red bubble chart on the bottom is the distribution of cases that have both data. The bubble size indicates the number of cases. Another chart we built to compensate the lack of detailed data is this cluster tracking map. It focuses on the newly discovered clusters and visualizes the geographic distribution of clusters by plotting them as tiny dots on a local map. As the result, this web page is the most popular data visualization story in Taobao's active news section. We stop updating the data for this web page when Singapore ends its circuit breaker measures on June 1st in a phased approach to resume activities safely. Although many other factors affect the page views, it got average 10,000 daily views for 2 months until the government stopped providing detailed data. The accumulated data and the customized visualization allow us to present more comprehensive insights and provide audience more engaging and exploratory experience. However, we also found that some audience fail to know that the answer they were looking for can be answered by playing with the filters. And some audience are reluctant to read a visualization that is not a bar chart or line chart. And some might get used to think a visualization is always static as print and fail to hover or click. Those literacy issues not only require design considerations, but also the data visualization education for journalists who produce the content. Thank you for listening.
Thank you, Liu Ying. I neglected to say that I believe you're working for Singapore Press Holdings. Is that right, Liu Ying?
Yes.
Yeah, so it must be very late for you.
Yes, that is great.
Thank you for coming. One question we wanted to ask was if it sounded like from your presentation that certain parts of the website were better understood or more visited based on the visuals that you use. And I was wondering if you could elaborate a little bit. Did you have data about how many users were coming and how they might have interacted with the site you created?
Oh, actually, it's a bit messy in the beginning because we don't know what will happen, and then we didn't expect that the cases will increase that much, or there's a global,
right.
So we didn't know what's the next we have to prepare for, and then so that's why we gradually implemented a lot of stuff. Sometimes remove some, sometimes add more, and also I think the government also had difficulty to put on these things, and they change their standard sometimes. Some data they not provide anymore, or they change their rules how to give those certain data. For instance, before they call the cases they cannot change the origin, call it unknown cases, and later they call it unlinked cases, which means as long as linked to someone, they see it as known cases. So we have to change that to calculate those data based on those needs, and also make it sense by design. And sometimes we get the feedbacks from the readers. They write to us, say, "Oh, why this data doesn't add up?" Or, you know, it's very difficult. But also we learn a lot of lessons from this by doing these things. Yeah.
Did you find yourself having to make trade-offs between sort of attention-grabbing aesthetic visuals and understandable and somewhat not interesting visuals, at least not immediately? Mm-hmm.
Exactly. For instance, you guys saw that spiral visualization. I think a lot of people say it's very interesting and got their attention. I guess for a lot of people, after you saw like tons of bar charts, then it's overwhelmed by a lot of those just charts. When you open a news charts and just get bored with that. So we are intentionally trying to do something interesting and get people attention, but at the same time, still want to make it make sense because our audience have to learn how to read the new charts always. It's very difficult to make decision. Where is the end? Like where's the boundary of this? How to balance it? Yeah. Okay.
Well, thank you for staying up so late to attend today, Liu Wang.
Thank you.
And thanks for your presentation.
Thank you.
Okay. And our last presenter of the session is Ab Mosca from Tufts University. And Ab will present a paper titled, "Does Interaction Improve Bayesian Reasoning with Visualization?"
Hi, my name is Ab Mosca and I'm with Tufts University. I'm here today to present our work, Does Interaction Improve Bayesian Reasoning with Visualization? I collaborated on this project with Alvitta Ottley from Washington University in St. Louis and Remco Chang from Tufts University. This project for us started with a conversation similar to this. Interaction is generally considered an improvement over static visualization, but is this always true? To start answering this question, we first turned to the literature and asked, is interaction always good? And what we found here were two sides of a coin. On one side, prior work supports interaction as a useful addition to visualization. For example, when it comes to exploring large amounts of data or for amplifying user cognition. However, on the other hand, some prior work expresses that interaction should be used with caution, and designers should really weigh potential benefits of interaction against potential costs. Now, before I go any farther, I do want to acknowledge that, in certain cases, interaction is indisputably good. So, for example, when I'm trying to display large amounts of data on a small screen, interactions such as zooming or panning are indisputably useful. However, what I want to highlight is that in these cases, interaction adds data to my visualization. In other words, it reveals previously occluded data or sometimes calculates an aggregate representation of underlying data. Our work, in contrast, is specifically interested in cases where interaction could help users reason with a static visualization. And so in order to investigate this, we decided to use Bayesian reasoning as a testbed, for two reasons in particular. One, Bayesian reasoning has been well established as a hard task. The canonical example of a Bayesian reasoning problem is this. I give you a base rate for breast cancer in the population. I give you false positive and false negative testing rates. And then I ask you a question such as, you get a positive breast cancer test. What is the chance that you actually have breast cancer? A lot of work has been done investigating how we can help people better perform this reasoning task. And that research has largely shown us that this task is hard. In a medical setting, it's hard for doctors as well as patients. And in visualization, there's been a ton of work looking at how we can visually represent a Bayesian reasoning problem to help people perform the task better. However, despite all this work, there's still no clear consensus on the best way to support Bayesian reasoning. The second reason we chose Bayesian reasoning as a testbed is because, on a basic level, it relies on communicating to the user 4 values: true positive, true negative, false positive, and false negative. So long as your visualization communicates these 4 values, the user has all the information they need to perform a Bayesian reasoning task. In other words, no additional information has to be added to the visualization in order for it to support Bayesian reasoning. So, given Bayesian reasoning as a testbed, can we empirically show whether adding interaction improves reasoning? To address this, we ran a 3x2 factor experiment. We tested 3 base visualization designs, and for each of these we tested them in an interactive and static setting. Our 3 base visualization designs, as shown here, range in the amount of spatial and alignment groupings they make to help communicate subpopulations of interest in the Bayesian reasoning problem. So for example, if you look at the grouped visualization here, you can see the have disease and do not have disease subpopulations are in 2 distinct grids. Similarly, you can see the test positive population is top left aligned in this viz. In contrast, if you look down at the randomized visualization, you can see there's no spatial or alignment groupings used to help communicate these subpopulations of interest. As for our interaction, what we did was take these 3 base visualizations and add interactive checkboxes to each of them. That looked something like this, where legend labels are now accompanied by an interactive checkbox. If a user unchecks a particular box, that subpopulation is no longer shown on the visualization. Notably, all of our interactive vizzes loaded with all 4 checkboxes checked off, meaning all subpopulations of interest were shown on the viz, and it was essentially identical to the static visualization. I also want to note that our intention with this interaction was to draw a stronger link between the textual and visual representations of the Bayesian reasoning problem. As for our experimental task, it was relatively straightforward. We asked people a canonical Bayesian reasoning problem. I'm now going to jump forward to our contributions. If you're interested in all of the different statistical analyses we ran in this project, I would encourage you to look at our paper for those. Our first contribution is a finding that participants assigned to the randomized base visualization had significantly worse accuracy on the Bayesian reasoning task with the interactive visualization than with the static visualization. If we look back at those 3 base visualizations, I just want to highlight again that the randomized base did not use any spatial or alignment grouping strategies to help communicate the different subpopulations of the Bayesian reasoning problem. So in comparison to the other 2 base visualizations, this visualization induces relatively high cognitive load. We postulate that adding interaction on top of this high cognitive load viz may have led to cognitive overload, explaining the decrease in performance we see with this visualization. Our second contribution is that our stratified analyses show the pattern I just described persists for people with high spatial ability, but not for people with low spatial ability. I want to go back to when we talked about adding interaction to the visualization, and I said our goal with the checkbox was to draw a stronger connection between the textual and visual representations of this problem. Now, prior research tells us that integrating text and viz can induce high cognitive load for people with high spatial ability in particular. We believe that's why we see a decrease in accuracy for high spatial ability folks when they're given the interaction, but not for low spatial ability folks. So in summary, what we've shown here is that in cases where cognitive load is high, adding interaction may lead to cognitive overload and decrease participants' performance on a Bayesian reasoning task. What I hope you walk away from this talk with is an understanding that we've shown in certain cases, a well-designed static visualization can be as, if not more effective as an interactive visualization. Finally, I'd like to thank my co-authors again, Alvitta and Remco, and to recognize the Walmart Foundation, DARPA, and NSF as our funding sources for this project. Thank you so much for being here.
Hi, am I saying your name well?
Just Ab.
Ab, okay.
Yep.
Apologies.
That's all right. It's an unusual one, so.
All right, thank you, Ab, for a really interesting paper. One question I wanted to ask, and this is a detailed question. Among those who interacted, did you look at their results as a function of visualization and spatial ability?
That's a great question. We actually did not separate out our analyses by people who interacted versus people who didn't. We found that only 40% of people assigned to the interactive condition actually interacted, which was interesting. However, when we were trying to decide how to handle our analysis, we felt like there wasn't a good way to individually look at people who interacted versus people who didn't without confounding our results based on just how diligent the participant was versus how diligent they weren't. Because we ran our study on Mechanical Turk, we felt like it was just really hard to separate out those two things. So that's something we definitely would like to look at further in future work. I think we would have to design the study a bit more carefully to be able to capture that fully.
Okay. Your conclusion that perhaps interaction should be a function of cognitive load is really interesting. And I was wondering if you have any thoughts about how to gauge the cognitive load that an potential interactive might have.
Yeah, that's a great question. Is the question. So in this study, as you're alluding to, we were only able to measure people's accuracy on the task. And then when we were trying to figure out why we were seeing these differences in accuracy, the conclusion we came to was that perhaps it's due to cognitive load. If you look into some multimedia learning studies, there's some evidence in that area that points to interaction being helpful for tasks up to a certain point. And then when tasks become too cognitively taxing, interaction, like you see a drop off and interaction is no longer helpful for those. So I think we could look into that literature a little bit more to try to see how they structure those studies and how they do their measuring of cognitive load. But that's definitely an area we're interested in going in, and we just haven't quite gotten there yet.
Right, and it's an interesting question too, because normally cognitive load, we think of it as an interactive thing, right? But it's staring at a static visual, isn't obviously a task going on, right? But it's interesting to think about how you might assess it just based on the static visual, right?
Yeah, it's a tricky problem.
All right, thank you, Ab.
Thank
nice
you.
Talk. All right, we have about 10 minutes to go in our first session, and I think what we might do now is go ahead and take general sets of questions. Please go ahead and put them into chat, either on YouTube or on Discord. And assuming that my cognitive load doesn't get overwhelming, we'll bring those to the speakers that are here with us. So let's take a minute while we give you a chance to type in some questions, or refresh them if they've scrolled away, and then we'll bring them back to a few of the speakers.
About having any thoughts about what affects a person's desire to interact with a visualization, but I think multiple presentations had interactions as part of their projects, and I wonder if this is. I think we can put this question to all of the speakers. Do you have any thoughts about what affects a person's desire to interact with a visualization? I encourage all of our speakers to pipe up.
Hi, Adriana, this is Nat. One thing in the reviews that we've done in terms of preferences, so which visualizations do people like the best that we've seen, is people typically like something that is familiar to them. So they may be more likely to say that they prefer, they like something. The caution that I want to provide that many people may or may not already know is that oftentimes the visualization people like the best is not the same as the one where they're best able to perform and understand. So I'm not as familiar with the literature about people wanting to interact with it, but that's what we found in terms of preference.
Did any of the other authors have thoughts about this? I did a study looking at, wasn't related to visualization, but looking at pregnant women and their use of a maternity education platform. There were all sorts of filtering capabilities where they could filter by gestational age or these different things to get information that would be more pertinent to them specifically. And none of them used it. They all just scrolled. So I've already experienced this myself. I don't know if anybody else has thoughts about this. Hi, Ab.
Hi. Yeah, I think I had mentioned in one of my answers that we found a very high proportion of our participants assigned to the interactive viz didn't actually interact with it. And we think, I mean, we kind of jump on the New York Times train a little bit in our assessment of the situation, which is to say, I think it's just people aren't necessarily interested in engaging with the visualization in that way. I think a lot of people go to these visual communication tools and they're looking for lack of a better phrase, a quick fix or a quick answer. And interaction, I think, can sometimes
sort of served up to them on a platter.
Yeah, exactly. Like what's my quick and easy, what do I do here? And I think interaction can sometimes feel like a bit of a detraction from that end to the user, as in like, oh, I have to put effort into this to get something out of it. Like, I don't want to do that. So that's our take on it.
Okay. Yeah, I can also see how the onboarding might make a difference, right? Depends on how
much instruction and push there is towards, by the way, here, try this, do this and see what happens. And maybe people just need more of a nudge. I've seen just yesterday, I think I was looking at one of the websites from, maybe it was one of the COVID dashboards, where you had to select a state before you could see anything. And so that's kind of forcing you to interact with the visualization in order to get anything out of it. Sometimes people might need that little nudge, but certainly when something is more relevant to us personally, like, well, what's it like in my home state? I want to see that. There might be a little bit more drive to interact with something than when you're trying to solve an abstract problem like Bayesian reasoning. Let's see. We have a question here about measuring cognitive load. Any, I know that you said you're in your paper, you measured visual analysis skills. Was that it?
So we actually in our study only measured
spatial ability.
Yes, we measured spatial ability and accuracy. So accuracy was the measure we collected from the task itself, and then spatial ability came from a follow-up survey. And so I guess to answer that question from the chat, we actually didn't directly measure cognitive load. We postulate that cognitive load could be an explanation for the results we saw, but we need to do follow-up work that explicitly measures that to be certain.
Alvitta, you made a comment on the chat. Do you want to actually show up on camera and say something?
Yes, like as the speakers are talking about interaction, the comment that I made is that I think it's important to consider the cost of interaction. And I think Heidi Lamis, who wrote a paper on this, so I remember like, maybe I have a vague memory of a paper that considers the cost of interaction. I think we need to do that more often. So Ab mentioned that in New York Times, they found that people just want to scroll. And if you have a very, very interactive visualization, then people won't use it. And so we need to start considering what are the different modalities of interactions, what are the costs of each one of these modalities, and perhaps depending on the design. So if we're looking at a more informative type of design, then we might have to consider the cost of whatever modalities that we use.
I had a thought about your paper when I was reading it, but I wasn't sure if I should bring it up because it's getting a little bit into the weeds. But I was thinking about how when you had the random view, which is the one where there was a cost, or rather you saw a decrease in accuracy because of the interaction. I wondered if if that could be explained by background and foreground effects, because you had a yellow box on a white background, and that if it had been a more saturated color, it might have been easier to spot and therefore harder to make an error in counting up, because you have to count up the boxes in order to do the division. John, please jump in and ask us a question.
Okay, great, thanks. I wanted to just bring in something that Alvitta just mentioned about costs, because the way I perceived that comment was on the cost of people's use of the tool. But I think especially for this session on visual communication, I think we're also thinking about different organizations who may not have the skill set or the people who could actually create these interactive dashboards. I can't tell you how many clients I have that say, we want a big website with interactive visualizations, blah, blah, blah. And you say, well, what are you trying to do? And they say, well, we're trying to tell the managers of our 8 food banks how many people they've had in the last week. And you're like, well, you just need an Excel file with like 4 bar charts. So I don't know, maybe that's more of a comment than a question, but maybe the question is specific for this type of track or session that, and this is specific to more of the academic researchers, to broaden the thinking a little bit about how organizations use data visualization and create data visualizations for their partners and their stakeholders.
I agree with you 100%. And I guess there's another way to look at Ab's finding, and that is that you might spend all this time developing these interactive techniques and people don't use them. And so perhaps it might not even be worth it, and they might not be more useful. So I agree that this is an interesting conversation to be had in terms of is it worth investing in an interactive visualization at all? Which is very controversial because I realize that the platform that we are at right now. But I agree, we should have these conversations.
Well, we are at 3:30 and I want to respect everyone's time. So let's come back at 4 o'clock. Anybody who wants to hang out and talk here is welcome to do that because we will be using the same channel, but we won't officially start back up again and delivering our content until 4 o'clock. Thank you.
Thank you, everybody.
Thank you.
Alvitta, I'll keep chatting with you if you want.
Morse complexes have shown a great utility in understanding the topology of complex scientific datasets. The noise in the scalar field, however, can significantly distort the Morse complex topology. Hence, we study the extraction of Morse complexes for ensembles of noisy scalar fields through their uncertainty visualization using our proposed statistical summary maps.
We present a flexible and easy-to-use software infrastructure for interactive rendering of large-scale display walls, either from on-site or from remote cluster. The display servers can easily be configured to support a range of typical network and display hardware configurations. The client library provides a straightforward interface for easy integration into CPU and GPU renderers. We also demonstrate this framework for use in deploying low-cost alternatives for display walls.
CarxS is an authoring system which enables rapid creation of zooming-based scatter plot-like visualizations in just tens of lines of JSON. We contribute a declarative grammar for such visualizations, which captures a large design space. By working with multi-node database spatial indexes, CarxS enables interactive browsing of billions of data points. Come listen to our talk to learn more.
Taylor-Coyle flows is a turbulent fluid motion created in the gap between the two rotating cylinders. The traditional reason-based methods are only able to capture the small-scale coherent structure. The detection of the large structure depends on the 2D cross-section, which is not the true configuration. We adapt the feature-level set methods and the density estimation to combine multiple attributes and use them as the filter to separate large and small-scale structure.
Deep learning models have become ubiquitous, but we often lack interpretations for their decisions. We developed a visual analytics system to interpret models that perform multi-class DGA classification. For each layer of the model, we visualize clusters inside its activation data, showing how classes and clusters relate to each other. In addition, we provide a decision tree to explain how these clusters are constructed.
Progressive visual analytics provides intermediate results in the middle of computation to address a long computational delay. However, such intermediate results are uncertain, so findings from these results can turn out to be incorrect for the entire data. In progressive visual analytics with safeguards, we suggest to risk the uncertainty, but we allow humans to leave safeguards every time they risk the uncertainty.
We present an algorithm for raycasting Hermite spline tubes, which result from letting a sphere trace Hermite splines that define its visual attributes. Since we do not employ tessellation, our method enables smooth curves and transitions of radius and color along the tube. Join us for an in-depth look at the intersection routine that enables raycasting hundreds of thousands of them efficiently in real time, and see what makes them a powerful new tool in the inventory of curve and line data visualization.
Ray tracing techniques can create images of astonishing realism and beauty. In the last years, the performance of those techniques has been increased significantly using dedicated hardware. Who thought that it's also possible to accelerate this? We show how to dramatically accelerate force-directed graph drawing with RT cores, yielding a speed up of 4 to 13x. If you want to know more, please see our talk.
CMed is a visual analytics framework for exploring medical image data annotations acquired from crowdsourcing. CMed can be used to visualize, classify, and filter crowdsourced clinical data based on a number of different metrics such as detection rate, logged events, and clustering of the annotations. CMed provides several interactive linked visualization components to analyze the crowd annotation results for a particular video and the associated workers.
As commonly known, dimensionality reduction techniques and their interpretations are complex, biased, and uncertain. In drug design, this highly complicates the search for similar and new chemical compounds. To overcome this issue, Canva brings comparison of different molecular descriptors and properties into one tool, featuring planar, 3D, and table views for evaluating the trustworthiness of high-dimensional data projection.
We present VIS, a tool for visualizing hypergraphs where edges can connect any number of nodes. VIS is the first technique to display hyperedges with no overlap or crossing. Vertices are represented as rows, time periods flow from left to right, and groups can be shown on the left. We designed the layout for readability. VIS shines with mid-size hypergraphs and it allows detailed analysis. We tested VIS successfully using publication datasets and data from historical documents.
Tableau helps you see the stories in your data. It's designed to help you be smarter, so you can make better decisions faster. With Tableau, you can keep on asking questions in the data until you discover the root cause. Share your analysis securely. Your entire organization can access these interactive dashboards from any browser or mobile device to find their own answers. Tableau. Answer questions at the speed of thought.
Ecosystems are complex and dynamic. To investigate the dynamic nature of ecosystems, we have developed a prototype of a visual analytics system based on empirical dynamic modeling, EDM. EDM is a set of analytical methods rooted in nonlinear state space reconstruction. Integrating EDM with dimensionality reduction, brush-linked visualizations, and visual summarization support understandings of ecosystem dynamics.
When visualizing data in a realistic rendered 3D environment, it is important to represent the data in a readable way. In our work, we investigate how the opacity affects the readability of a 2D shape and determine useful opacity ranges. Therefore, we performed a user study with different overlay configurations like filled, striped, and dotted pattern, their density, and considered the effect of an outline.
When developing a deep learning model, people typically struggle to optimize hyperparameters that affecting the model performance. To relieve the pain of this manual trial process, AutoML has been developed as a solution. However, to maximize the potential of the AutoML, people should identify a good AutoML setting for their task. HyperTendril helps to maximize the potential by visualizing AutoML algorithm behavior and guiding effective hyperparameters.
Billions of biologging records reflect animal behaviors on many temporal spatial scales, yet segmenting the time series on multiple scales is often avoided or impeded. Hence we present our MultiSegVA platform with its three contributions. First, MultiSegVA contributes tailored visual interactive features for multi-scale segmentation. Second, we show a new visual query language to flexibly configure scale-wise techniques and parameters. This VQL consumes a domain-oriented set of techniques, our third contribution.
We present StratGraphics, an approach for designing data-agnostic and fully reusable visualization templates. StratGraphics follows the inverse workflow that common data-driven systems. Rather than starting from data, designers construct visualization structures without relying on a data schema. Data tables are shaped later from the structure of graphics. We demonstrate the power of the approach through a gallery of visualization examples.
Spot SDC is a visualization system that helps researchers understand the resiliency of HPC computation kernels to silent error corruptions. It gives users multiple perspectives of details with different granularity about the impact of SDC on an application's output. It also provides novel insight into how silent error propagates through a program's execution.
We present the first generic design space and library for visual piling. Inspired by physically piling paper documents, visual piling describes an interface for spatial organization of visual artifacts into piles of partially overlapping items. Piling affords interactive grouping, arrangement, previewing, browsing, and aggregation to reduce the complexity and support comparison of large collections of small multiples.
Nowadays, online services are used for all kinds of activities. Strategies to increase the situational awareness of personal data stored by online services are needed. We present Transparency VIS, a visual, interactive web application. It allows common internet users to explore their personal data exports, which can be requested from online services like Facebook, Google, Instagram, or Twitter. Feel free to try it out online.
Attention mechanisms have greatly improved the performance of many language models. Yet with great power comes increased complexity. In this work, we present attention flows, a visualization that let users interpret the language model's decisions and gain insights into the underlying self-attention mechanism. We also support model comparison that helps to fill the gaps between models in different training stages.
We present Lyra 2, a system for designing interactive visualizations by demonstration. To design interactions in Lyra 2, users directly manipulate the visualization canvas. The system interprets demonstrations using heuristics and suggests possible interaction designs. We find that Lyra 2 enables rapid prototyping of an expressive range of interaction designs. We're excited to share this work with you.
Suppose you want to see the overall commit structure of a new project repository. Using Git client tools, GitHub Network, or Git log command, it's quite burdensome to get overview and navigate data. We presented Gitthrough as an interactive visual analytics system for the Git metadata to help users explore and understand the context of development history.
How do you visualize the nanoscale, 1/1000th of a meter, for the public? As part of a Science Center exhibition, we developed an immersive environment that explains nanoconcepts by allowing users to explore nanoproperties. We reflect on how exploration, the confluence of explanatory and exploratory visualization, can be applied to visualization in public spaces.
Transitions are widely used in data videos to build seamless changes between video narrative. As the attention cue, they can not only keep viewers oriented but also express narrative information. After conducting a content analysis on the transitions in the dataset, we provide a comprehensive taxonomy of narrative transitions in data videos.
The ever-evolving landscape of malware detection and evasion creates a constant catch-up contest between the defenders and the adversaries. We created a system which submits and analyzes a malware sample with Cuckoo Sandbox and then animates the battle between the malware and the anti-malware system. The Gotta Evade 'em All system is a useful tool that uses a familiar concept based on Pokemon, allowing the understanding of malware evasive behavior to be more accessible.
Entities and their changing relationships can be modeled more precisely as temporal hypergraphs, but hypergraph models are difficult to explore and refine. By leveraging domain-specific geometric deep learning models and a new multi-level hypergraph visualization, our technique allows for the direct integration of domain knowledge into the machine learning process. The multivariate hypergraph model structure can be analyzed on different abstraction levels. Simultaneously, experts can integrate their domain knowledge on the fly, and then explore the refined machine learning model.
Analyzing urban heat island phenomena, which cause higher temperature in cities, requires to explore the relationships between climate and urban morphology. In an ongoing co-visualization framework, we propose different ways to visually explore both urban and climate data at a city block scale in order to support the analysis of urban heat islands.
This is a picture of a Tableau visualization within the browser. The data behind the visualization does not exist here, and Tableau is not running. This is just an image. However, parts of this image are fully interactive. Please join our presentation to see how we can share interactive visualizations across the web, free from any dependency on data or visualization application.
The transport dynamics in an unsteady flow can be visualized by the finite time lab on a fixed exponent. But what happens if the flow contains random Gaussian deviations? We introduce a recently published quantity that is similar to the FTLE but considers these stochastic deviations. We discuss the application to real-world data, compare it to prior methods, and present a complementary visualization.
With the proliferation of AutoML systems, it's now easier than ever for non-experts to create and deploy end-to-end machine learning pipelines. These systems explore the model search space and optimize hyperparameters in order to solve a particular task. We propose Pipeline Profiler, a tool that enables the exploration and comparison of machine learning pipelines produced by multiple AutoML systems. By analyzing these pipelines, we have the opportunity to better understand how AutoML systems work and obtain insights that can be used to improve them.
We present NL4DV, a toolkit that helps prototype natural language interfaces for data visualizations. NL4DV provides a high-level Python API for interpreting natural language queries. The API automates the core tasks of processing natural language queries to infer relevant information and determine appropriate visualizations, allowing visualization developers to focus more on designing and implementing the user interface.
Data videos are quite popular nowadays. They usually show changes in the data. However, creating a data video requires multiple skills, and the process is usually laborious and iterative. Our approach focuses on automatic and interactive visual enhancement of important changes in time series data with data video.
Welcome back to the workshop on visual communication, or visualization for communication, I should say. This is the second session, and we're going to have some really interesting paper presentations again here. We already had a very good discussion here during the break, so we also have a few things that I should point you to continue this discussion and to continue the workshop. So at the website, or on the website, I should say, VisComm.io, that is also linked in the notes right under this video that you're probably watching on YouTube right now. You can go there. There's now a link to that mailing list or Google, And also, we have a meetup on Thursday that we should mention again at the end of this session, but that also should be linked from that website. So the VisComm.io is the place to go to find all that information. And with that, we're going to just start right into our first paper here, which is titled Variable Biases, a study of scientists' interpretation of plot types commonly used in scientific communication. And this is by Laura Madsen, Christine Dees, and Deb Ronan.
Hi, I'm Laura Madsen of Sandia National Laboratories, presenting the paper Variable Biases, a study of scientists' interpretation of plot types commonly used in scientific communication. So in scientific communication, it's often very important to represent the uncertainty or variability in a data set, but that information can be very tricky to visualize. First of all, it can be really difficult just to characterize the uncertainty or variability because it can have lots of different sources and causes. Even if you have a good characterization of the variability in your data set, that information can be difficult to visualize because it might involve adding extra cues to the plot that could be confusing or cluttering. Even if you do a great job with the visual representation, the viewers might bring their own cognitive and perceptual biases to bear, and they could misinterpret the visual cues. There's some prior research indicating that even experienced researchers commonly misinterpret cues as simple as error bars on bar graphs. So how can we start to address this complicated problem? One thing we can do is bring to bear research from the cognitive science community in setting up controlled experiments to look at how people interpret the same underlying data sets when they're visualized in different ways. So we did an experiment looking at statistical graphs. We had participants who were experienced researchers looking at the same data graphed in different ways. And we compared how they assessed the differences between the two data sets in the graphs and how that changed for the different types of visual representations. So our starting point was looking at bar graphs with error bars. So prior research has shown that these are widely used, widely understood. People tend to have high confidence when interpreting bar graphs. However, they're also subject to known biases, such as within the bar bias, where people judge points that fall within the bars as being more likely than points that fall outside of the bars. Also, as I mentioned before, even experienced researchers frequently misinterpret error bars on bar charts. So what are some other visual representations that can mitigate some of those biases? One of them is scatter plots or dot plots. Those show the data directly, so that reduces the opportunities for biases in interpretation. But the central tendency is not explicitly marked, so they might not provide good support for the task of comparing two data sets. They're also not feasible for large data sets as the number of dots grows too large. Box plots explicitly encode the median, upper and lower quartiles, extremes, and outliers in the data set. But the problem with box plots is that different distributions can produce identical box plots. Violin plots attempt to get around this issue by encoding the distribution via the width of the bar. They've also been shown in prior studies to mitigate within the bar biases. We might expect people to perform better with violin plots than with bar plots. We did an experiment to test this. We had 15 participants from the University of Illinois community. They were all experienced researchers who were authors of at least one scientific paper containing graphs with visual representations of variability. They had an average of 8.7 years of experience in research requiring statistical inference, and all of them could accurately explain to us what it means when a t-test has a p-value of 0.01. We asked them what visualizations they most commonly use in their own work, and most of them use bar graphs, a handful use scatter plots, line graphs, or violin plots. For our materials, we had 20 unique pairs of data sets that were created and arbitrarily labeled A and B. The data sets were constructed so that when we conducted a two-tailed t-test comparing A and B, the p-values fell in one of these 5 ranges. So we had equal numbers, 4 data sets falling into each of these ranges. These 3 are statistically significant when compared with the t-test. These 2 are not. So we had these data sets, and each pair A and B was plotted in 6 different ways to create a total of 120 stimuli. So these were the 6 types of plots we used. we had two types of error bars, 95% confidence interval error bars, and error bars that showed the standard error of the mean. We have box plots, jitter dot plots, density plots, and violin plots. So our procedure, we collected participants' eye movements using a Smart Eye Pro eye tracker. Each trial began with a 1-second fixation cross, followed by the visualization being presented for up to 10 seconds. When they advanced, they answered two questions. First being, is the difference between groups A and B statistically significant? And they clicked yes or no. And then how confident are you in your response? And they clicked answer on a Likert scale from 1 to 5, where 1 was not confident at all and 5 was very confident. So what did we find? The participants were significantly faster, more accurate, and more confident in their responses for the bar graphs relative to the other types of graphs. And for the record, the error bars I'm using in my plots here are showing the standard error of the mean. So we see that participants had a higher average accuracy for the two types of bar plots, and they were also more confident with the two bar plots. Similarly, for the reaction times, the participants had the fastest response times to those two types of bar plots. We had predicted that participants would do best for the extreme p-values. We found that to be the case across all the different types of graphs. And we see the same pattern over and over again. But there's an interesting difference here when looking at the two types of bar graphs. And again, bar graphs were where people did the best, but we see a different pattern of performance when we compare those two. On the next slide, I'll break that out so we can see this difference more clearly. So at the ends of the extreme ends, participants were equally accurate with both types of error bars. But in between, for the differences that were statistically significant, they performed much better for the standard error bars than for the confidence interval bars. For the differences that were close to being significant but not quite, they did well with the confidence interval bars and very poorly with the standard error bars. So in other words, the participants consistently misinterpreted the confidence interval error bars, saying that the significant differences were not in fact significant. And then the opposite pattern of misinterpretation for the standard error bars, saying that the difference was significant when it was not. The eye tracking results showed that the participants had fewer, longer fixations for the bar graphs than for the other types of plots. These shorter, more numerous fixations for the other plot types are indicative of visual search. So that indicates that the participants, just like how they were more confident with the bar graphs, they knew where to look and they didn't spend much time searching around the graphs. For the other plot types, their eye movements indicate more searching for information. Since the two types of bar plots have the same visual features, we can compare the proportion of fixations to regions of interest. What we found here was that participants had significantly more fixations to the confidence interval error bars than to the standard error bars. And this corresponds pretty well to their confidence ratings. So they were more confident with the standard error bars. They spent less time looking at those. They spent more time studying the bars in the case where they were less sure of how to interpret them. So what did we learn? Basically, we found that visualization type influenced the participants' accuracy, response times, confidence, and eye movements. The bar plots supported the best performance for this task, partly because they explicitly encode the information that is important to the task, and they're the visualizations that the participants were most familiar with. So it's important to note that the box plots also explicitly encode all the information participants needed, but participants didn't perform very well with those and indicated that they're not familiar and don't use box plots very often. So even though bar plots did the best, we found systematic biases in interpretation of the error bars, consistent with prior results, where people tend to be overly conservative with confidence intervals and overly lenient with standard error bars. So just to summarize, there's a complex mixture of factors that come into play when people are interpreting data visualizations. So people's tasks, prior experience, their familiarity, low-level visual features, and visual spatial biases all interact with one another in complex ways. But if we do carefully controlled experiments, we can identify systematic patterns in how viewers interpret visual cues. And that can be very helpful for helping us understand and mitigate perceptual and cognitive biases, and in turn to develop better visualizations for scientific and other communication. Thank you very much.
I need to unmute myself, it turns out. All right, so thank you very much for this talk. I still haven't learned Zoom even after months of doing this every day. So before we start with questions, I just want to say that if you have questions while you're watching these talks, please either go to Discord, which is linked from down below somewhere in the description of this video, or to one side of this video. I think it's probably this side. There should be a little box where there's discussion happening, and there you can post your questions. So the first one we have here is from Ben Watson, who asks, so your work has very highly educated participants, and yet they did not do very well on the alternatives to the box plot. Should we abandon those alternatives? And if not, what can we do with those alternatives, and when should we use them?
Yeah, so I think one of the key takeaways from this study is that people's familiarity with the plot types is really important. So some prior research has found that the general audience can do better with violin plots when asked to compare two different distributions, which was part of the inspiration for this work. But then using these participants who are experienced researchers who make bar plots all the time, they really did much better with those than with violin plots. So taking that experience into account when designing plot types is really important.
Mm-hmm. And so relatedly, we have a question from Molly Hurst, which also something I was thinking about is about familiarity and training. So she asks, do you think that your results would have differed if you had trained people on the visualizations that they weren't familiar with and that they didn't know as well?
Yeah, I think that could help. That's something we'd like to investigate more. If you give people training, does that help them? Would that bring, say, violin plots up to similar performance as bar plots?
Mm-hmm. And then finally, Adriana asks, do you think that people would make more accurate judgments with formats such as density plots if central tendency were explicitly marked?
I think so. So having things that are relevant to the task being explicitly marked definitely seems to be one of the key factors in terms of what plots perform best. So yeah, if you know what kind of task people are doing, being able to mark those features is very useful.
And there's a little, I can't talk right now, sorry. There's a little connection here with the previous session on interaction. So I wonder, have you thought about interaction at all? Like how interaction might help in this case?
Yeah, that's a really interesting question. I was thinking about that during the first session too, because we were focusing on the types of visualizations you'd see in a paper. So we were only looking at static viz, but adding the interactive, like on a website where you could have interactive visualizations, that could really change how people use these types of plots. So yeah, I think that's really interesting kind of future direction.
Mm-hmm. Excellent. Well, thank you so much again. And we'll move on to the next presentation, which is a visual case study titled How Do Taxes, Benefits, and Public Spending Evolve for a Taxpayer During Their Lifetime? And this is by François Lévesque, Luc Goubot, Michael Aubert-Aucher, and Thomas Urtu.
How do taxes, benefits, and public spending evolve for a taxpayer during the lifetime? This visual case study was conducted by the Research Chair in Taxation and Public Finance from Sherbrooke University and visually designed and developed in collaboration with Polytechnique Montréal. One of the chair's main goals is to analyze the socio-economic aspects of taxation and public finances and to disseminate its research results to a general public audience, and more specifically, Quebec citizens. This project explores a narrative format accessible to the general audience to answer how do taxes, benefits, and public spending evolve for a taxpayer during their lifetime. It is based on a thorough analysis of both the tax levies, including consumption taxes, as well as tax benefits and the monetary value of public services, such as national education, healthcare, childcare, etc., obtained over a lifespan for a Quebec province household. This analysis showed that 3 different average life stories, depending on the life events that can affect an household, studies, changes in the size and composition of the household, are reasonable ways to give representative and accessible answers to the title questioned. We follow Ella, through 3 different realistic financial life stories. Scenario 1. Ella lives alone, without children, throughout her whole life. Scenario 2. Ella starts a relationship at 27, gives birth to 2 children, and remains with her partner until his death. Scenario 3. Ella starts a relationship at 27 again, gives birth to 1 child, and parts ways with her partner when she reaches 40. Ella has the sole custody of her minor child and remains single for the rest of her life. The main goal of the project was to visually explain to the public how and why benefits and public spending change for each one of these scenarios. More specifically, the communication objectives are: communicate evolution of taxes, levies, benefits in detail over time. We want to compare those evolutions for each scenario. We want to engage the readers by telling a story, decomposed in recognizable periods of life. We also want to communicate a cumulative record of what has been received and what has been paid over a lifetime. And fifth, we allow seasoned readers to optionally dive deeper into the data. One of the first design considerations was to communicate the amounts with histograms. The visualization model was chosen since length and position are one of the best channels to convey precise scales. To easily compare the 3 different scenarios, we positioned the histograms side by side using a small multiple. To better communicate the evolution of amounts, we used a scrolly-telling interaction combined with animations. On bigger screens, the free space is used to display the detailed amounts on bar charts. On mobile, these bar charts are removed and the histograms are disposed vertically. Let's do a quick demo. At first, each scenario is explained in detail so that the user understands what he's looking at on the next screen when he scrolls down. We then see all the histograms and the bar charts side by side on 3 columns. Each time we scroll, we can see a small text explaining the current events we are looking at during the life stories. For instance, here we are exploring the first years of college of Ella. We go through all the different amounts. First the salary, then the tax levies, then the benefits, and finally the public spendings for school. Each time we hide all the other categories and highlight a specific category. Next, we see the beginning of the career at 21 years old. We go through all the amounts in details. And then she starts her life as a couple. So in scenario 2 and 3, the amounts are slightly different. Indeed, the salary is twice as big because now the household is composed of 2 people, Ella and Luis. We then explore how and when benefits and public spendings change according to the children Ella has. We can see in scenario 3 that Ella part ways with Luis. So the salary in scenario 3 is cut in half. And we then go through retirement and finally the end of life. Over the course of a lifetime, Ella's 3 households are assisted by public services, perceive benefits, and in return they pay levies. We can now observe all these amounts in one place. By calculating the difference between what has been perceived and what has been paid, it is possible to observe if Ella's household has made any net profit or if it's a net contributor. We can see that in specific periods of time, Ella receives more than she pays, especially when she has children or when she's living alone with her child. The annual accumulation of the benefits and levies allows us to evaluate for a specific year the cumulative difference between, on one end, the amount of the benefits and public services perceived during adult life, and on the other end, the amount of levies paid. We can see that in scenario 2, Ella's household start to obtain more than what they paid over the course of an entire lifetime, sooner than all other scenarios. At the end of the scroll retelling, a seasoned user can inspect the data in more detail if he wants. He can inspect each one of the bars in the histogram. He can use the handle on the side to filter by age, and as well use the inputs on the left to change minimum and maximum age. He can turn on and off incomes, benefits, public services, and levies. He can also see the difference between the benefits and public services and the levies. This visualization format has been visited by around 2,000 unique visitors during the month following its release. It has also been covered in at least 3 daily newspapers and magazines. The demo is available on livestories.netlify.app. If you have any questions, feel free to ask. Thank you.
Excellent. Thank you so much. So we have Francois here who can answer some questions. So one was by Adriana about the impetus behind this project. Can you tell us a little bit more about the goals?
Yeah, the goals of this project. First, you know that this project was made in collaboration with the chair of public finances of Université of Sherbrooke. And one of their main goals is to communicate the amounts taxation information to the large public. So this project was sort of a direct response to this objective. So the main goal was to communicate how the levies, the benefits, and the public spendings, those three amounts, fluctuates over the lifetime of a person, depending on what they live through the life. So if you have a child, if you get married, all these things have a huge impact on how much you pay for the government and how much you receive from the government. So that was the main goal of the project. And it's quite complicated to understand from a layperson, but once you digest it a little bit more, you can make it a little bit easier to understand for everybody. So that was the main goal of the project.
Mm-hmm. Excellent. Mm-hmm. And very quickly, because we're going to have to move on to the next talk, but the other question that Ben asked is, can you tell us a little bit about the public reaction to your site and what you found to work well and not so well?
Mm-hmm. Yeah, we received great feedback from a few users while designing and testing the tool. However, we didn't conduct a proper user study to evaluate the efficiency of the tool and to compare it against other techniques. But what I can tell is that the scrollytelling technique was very efficient to guide the user through all the different amounts, since we can hide some portions of the screen and really focus on specific amounts. But something a little bit more hard to understand was the accumulation of amounts at the end was somewhat more difficult to understand, to grasp, maybe because it's a arithmetic operation, so we need to understand the math behind it. So that was something a bit more difficult to show, maybe using more animations to kind of explain the math behind this would be a better way to communicate this.
Is a visual case study. Again, this is the second visual case study we have, and it's titled Tile Narrative, Scrollytelling with Grid Maps by Pratap Vardhan.
Hi everyone, I'm Pratap Vardhan. I hope you're doing well and staying safe. In this video, we wanted to explore the idea and motivation behind tile grid narrative. So through this visual case study, we wanted to study the effectiveness of using both tile grids and scrollytelling together. To begin with, humans and maps go a long way back. We have been mapping since ages, and maps are one of the most popular forms of visual representation that most people are exposed to. Hence, play a huge role in dissemination of ideas, and in general, they have become the de facto choice for visualizing geospatial data. And you must have already heard of choropleth maps, which have emerged as a go-to method to visualize geographic data. In this particular type of chart, what and where we show as color tends to cover the entire area. And this is useful for when area is a metric, for problems like understanding forest cover, spatial distances, and so on. However, sometimes choropleths can be misleading. Choropleths tend to skew attention towards bigger states, areas, or blocks or entities. So the problems we typically face are the areas are not usually scaled to data, the geography distorts these patterns, and you can't accurately differentiate the comparison between entities. For example, see this famous yet puzzling map of US 2016 voting patterns for the presidential election. By the looks of it, it appears the Republican support, which is in the shade of red, is at least 3 or 6 times that of Democratic Party, which is in the shade of blue.
It also appears large swathes of land in this part in the north seem to have same importance as this portion of land in the right. Hence, some data stories need equal emphasis for geographic entities and be arranged in a way that is close to the actual map representation. For example, cartograms are one such way, but they are difficult to interpret. Shape is heavily distorted, and since we are so used to seeing maps, we need something that makes regions placed closer to where we live. Tile grid maps handles this problem optimally. As you can see, map areas are given a uniform size and shape, usually a square, and they are arranged to approximate their real-world position. Northeastern states appear to have similar significance as the West Coast. We could also treat this as a small multiple visualization. Once you have these units, the underlying chart can be a simple bar chart or a trending area chart or a custom bespoke visual like on the right. Now, lately, visual storytelling has emerged as one of the most effective storytelling techniques to engage users. Now, this is a technique wherein the content or graphic on the web page changes as the user scrolls up or down. This form of storytelling technique is quite popular in data-driven journalism field. What we propose as tile narrative is nothing but a fancy way to merge tile grid maps and storytelling together and use automated narrative insights to explain the visual. Let's walk through an example to see how this breaks down. In this visual story, we wanted to understand how states across the US have limited their movements to different places since COVID-19 outbreak. Now, let's look at some of the critical visual elements. We have all the US states as small multiples, and each state is represented by an area chart, which shows mobility trend. Now, color here represents the latest mobility percentage. Now, for a curious reader, we also provide micro details like the latest value and use this text element on the top as a tooltip and change the value as the user moves the mouse over the trend of the unit. Next, as the user scrolls through the story, insights from the story are revealed as narratives. These narratives are auto-generated from data. For each of these narrative elements, whenever it comes into the active viewport, an event is triggered to update the visual state. Active state is picked up from the narrative, and the map then zooms into the specific state of interest. As the next narrative comes up while scrolling, the main visual transitions the viewport to the state of interest. You are also provided a drop-down to select different metrics, and narrative insights are automatically generated based on pre-configured pattern rules. And as and when the mobility data is updated, these insights would also change, and that too happens automatically. This is how you can use the tile narrative to set up a story. We first draw a small multiple tile grid map. Then we construct narratives from data based on the rules we think could be repeatably used for the story. Then we link each narrative insight to a tile via a state identifier. Now we evoke a trigger event, in which case a state key, as and when you scroll into that particular insight. And that zooms the map into the tile of interest. The two primary components that needs to be built are charts and scroll events. I have used D3JS for charts and scrollma for storytelling. You could implement the same with other libraries as well. Now, we auto-generated the narrative text in this example. Upon understanding the nature of the story we wanted to tell, we structured the patterns or the rules by answering questions like how many regions are better off now compared to the past, or what are the number 1, 2 regions with the highest gain in mobility or with the highest drop in mobility. Also, how do states like specific ones like California or New York compare with their neighbors? Although I have automated the textual insights with data-driven rules for the mobility story, you can actually handcraft these insights and decide the flow of the story. And here's the second story we did to understand how COVID-19 pandemic affected the unemployment levels across the country. This data comes from the Bureau of Labor Statistics, and we looked at the time frame between January and June 2020. We were able to measure users' interactive behavior on the page and gather some feedback. Most users paused and spent time to read the insights, which we think links to engagement. And several users indicated they were able to recall the insights for a longer time. And users who are mostly exposed to KPI reporting dashboards also expressed need for more controls to explore the story pretty quickly, as opposed to a long form narrative. An area of improvement could also probably be a more controlled and smoother transition through narratives while scrolling through the grid, because it seems to hang up a little bit. As far as the next steps are concerned, we are presently investigating different data sets to see what chart types that we could play around with for different stories and understand different narrative patterns that can be automated in a way that we can make this format generically available. And with that, I conclude my presentation. Here's the link to the paper and the interactive. Please reach out to me if you would like to learn more. Thank you for your time.
All right, excellent. Thank you for the presentation. I have to say I've been a bit lenient with question time for the last few talks, so we'll need to cut this a little bit shorter and be a bit more efficient. So I'm going to just ask you one quick question, which is, have you thought about, so Adriana asks, have you thought about color schemes that diverge at 0 for those charts that have positive and negative numbers?
Yes, I mean, in cases where what I was primarily focusing on was to emphasize on the ones where you need primary attention, but not to focus on states that necessarily might have better rates to it, especially the ones that we're talking about COVID. So I guess the choice was there largely to focus on the states where the growth rates were pretty higher. And that, for that particular reason, we didn't really choose the colors where you might have to pick between diverging colors. I did for the next case study in which the unemployment numbers were being discussed. I think there we did choose between two different sets of colors for positive and negative ones.
Mm-hmm. Great. Well, again, thank you so much. And we're going to move on here because we need to make up a little bit of time. So sorry about that.
Sure,
but we have more discussion, of course, in on Discord. So feel free to chat there as well, of course. And the next presentation, I should say, is a visual case study again. This is our third and last one. And this is titled Analyzing Dorian Twitter Data to Understand How Hurricane Risk Communication Changes as Threats Unfold. And this is by Catherine Ma and Barbara Millett.
Today, I'm gonna introduce you my visual case study, analyzing Twitter data to understand how hurricane risk communication changes. I'm Catherine Ma. I'm the second-year PhD student from the University of Miami. I'm from China. I used to be the data journalist and information designer. For this study, I cooperated with Dr. Barbara Millett. She is the director of the University of Miami UX Lab. For this presentation, I'm gonna briefly introduce you my visual case study, the methods, the findings, and the Flourish demo. Communicating effective hurricane risk messages on social media present potentials, also challenges, especially for Twitter, which is regarded as one of the prominent platforms to disseminate hurricane risk information. For previous study, we found that there are two main directions. One is to examine hurricane risk communication patterns across the whole pieces. The other one is to evaluate the communicators' engagement. So there comes a knowledge gap, that how hurricane risk communication messages are disseminated through the hurricane-related social network on Twitter. So this is gonna be our research focus. We chose Hurricane Dorian because it is the first major hurricane during the Atlantic hurricane season last year, and it is also considered the most powerful hurricane that striking the Bahamas. We mainly focus on three questions. One is the types of forecast messages, who posted, and when they are posted. The second question is about professional accounts engagement and their interaction with each other. Finally, it's about tweet sentiment. We collected more than 20,000 tweets across the whole time frame, ranging from the October the 20th to the September the 10th. The tweets included original tweets, reply tweets, and retweets. Two kinds of accounts have posted the tweets. One is organizational accounts, which includes the primary accounts like National Hurricane Center and National Weather Service and other weather-related organizational accounts. The other one is the professional individual account, which includes the professional individuals like meteorologists, the weather scientists, and climate scientists. So for the question 1, we first did the descriptive statistical analysis to show the basic trends across the time frame. Then we designed cross-matrix coding scheme, which include message functions, message content, and media forms. We manually coded all the original tweets and identified their message pattern. For the second question, we focus on the network analysis of these professional accounts to see how they interact with each other. For the third question, we did a sentiment analysis of the original tweets and the user replies. So, for the first two charts, we illustrated our descriptive statistical analysis. As you can see for the first one, we encoded the tweets type, original reply retweets with colors, and distributed them with dimension of time and total account. So as you can see that original tweets and retweets got the most at around the September the 1st, because on that day, the Hurricane Dorian reached to the highest category, level 5. This is another way to visualize the whole data. We categorize the tweets based on its creator's account, and then we encode the amounts of tweets with sequential of blue color, and finally distributed them across the time frame. At the end of the first research question, we had manually identified the message pattern and visualize it with a Sankey chart. The first column is the message function, which includes the forecast messages, associated impact, and reminder. And for this side, the third column stands for the media format the message are. And in the middle, this is the information element that belongs to different types of messages. For example, for the spatial and temporal element, it belongs to the forecast messages. Also, it shows up in media formats like information panel and radar animation. The next three visualization answers the second questions about social networking and the professional accounts interactions. So as we all know that there are three kinds of social media engagement: the retweets, mention, and reply. We categorize these accounts into emergency management, forecast organizations, mediator, and others. So as you can see that compared to the other two engagements, mention and reply, most of the accounts are more likely to be active in retweeting others' tweets. Final three visualizations answers the third questions about the sentiment analysis. So for the first one, we calculate the average sentiment score of the total tweets for each hour every day and distribute it across the time frame. You can see that the negative sentiments shows up in the very beginning. However, when the Dorian came to the highest level at the September the 1st, the average sentiment score tend to be more neutral. For the second visualization, we calculate the average sentiment score of all the tweets posted by original accounts and professional individual accounts. So as you can see that at around September the 6th and the 7th, when the Dorian made its landfall in North Carolina, the sentiment score tends to fluctuate a lot. Then we explore the relationship among the sentiment score, the account type, and account followers. So we encode the amount of followers of each account with the area of square and calculate average sentiment score of each account based on all of the tweets they have posted during the Hurricane Dorian. So at the end of the research, we tend to explore the relationship among the message type, retweets, amount of mention, and amount of item one message included, and also the sentiment. So we made this multi-dimensional scatter plot with the log scale y-axis. So for the item part, we encode the amount of every item that every message is included with circle area. For the second one, we encode the amount of mention with circle area and make this distribution. For the third one, we encoded the average sentiment score with each tweet with the circle area and made this distribution. Our research is important because we need a bridge between the primary account and the general public account. Not every important hurricane risk information can reach to the general public without this bridge. From our research, we found that the communication among the hurricane risk-related accounts are more likely to rely on the post-timing and the accounts of expertise. Besides, the hurricane risk information can be improved as the rapid development of advanced forecasting techniques and capability. So for our future research, we plan to explore more about dynamic changes in risk messaging, the influential factor of the social networking, and also we're curious about communication patterns among the hurricane-related accounts. And we're also interested in explore communication patterns and visual analytic approach to detecting risk message themes. So thank you for listening to my presentation. If you have any questions, please let me know. Thank you.
All right, thank you so much. So we have one question from Ben Watson here about the intended audience for your visualization. Who are you aiming at with this work?
Well, you mean the viewer case? Well, I think that this is just the in-process model. We're just making it, and I think the potential audience is maybe the strategy maker, or like some organizers or some relevant stakeholders from the government or from the Hurricane Risk Center or other kind of researchers about the weather forecast, or yeah. So I think that this is our viewer case study have provided kind of potentials to develop a real system, a real textual analysis based system to do this kind of Twitter post analysis. But there are a lot of difficulties have to overcome. So yeah, like natural language processing, or like how to identify the kind of patterns, language patterns of this kind of hurricane risk forecast. So yeah, this is just provides some kind of potential, I think.
Mm-hmm. And very quickly, do you have a sense of how this compares to other other natural disasters or other events where how people are communicating? Do you have a sense of how this case study compares to those other ones?
Yeah, we have a plan to do that. Yeah, we have plan to do that. And actually, I think that this kind of research is rare. I have read a lot of literature say how they communicate about earthquake, or how they communicate about other kind of hurricanes, but that's it. There are not a lot of kind of natural disaster communication out there. So yeah, this is our plan. Yeah.
Okay, excellent. Yeah, maybe for next year's VisComm then. All right. So with that, we'll move on to our final paper. And this one is titled Beautiful Visualizations Slain by Ugly Facts, Redesigning the National Hurricane Center's Cone of Uncertainty Map. And this is work by Barbara Millett, Alberto Cairo, Sharanya Majumdar, Caroline Diaz, Scottney Evans, and Kenneth Broad.
Hello, my name is Barbara Millett. Today I'll be presenting our paper titled Beautiful Visualizations Slain by Ugly Facts, Redesigning the National Hurricane Center Cone of Uncertainty Map. Our interdisciplinary team, Hurricon, draws from a number of fields, including meteorology, environmental anthropology, data visualization, human factors, interface design, and community engagement to address a critical gap in visual hurricane forecast products, making them easily understood by the public. Thomas Henry Huxley once said that the great tragedy of science is the slaying of a beautiful hypothesis by an ugly fact. We feel that a similar claim can be made about visualization design. No matter how well made and beautiful a graphic is, even if it follows best practices, it will sometimes be slain when tested against the reality of its readers. However, even when a design fails, there's still an opportunity for learning and informing future iterations of the product. When a hurricane threatens, people access information from different sources to evaluate their risk and make decisions. The Cone of Uncertainty is the most widely used graphic by the media and the general public. It is created by the National Hurricane Center, provides forecast track of the center of the storm, together with an estimate of track uncertainty, and also depicts areas under watch or warning. Technically, the Cone of Uncertainty represents the area within which the center of the storm has a 67% chance of appearing based on a 5-year mean track error. Notwithstanding its widespread use, the graphic has several shortcomings. The graphic is overloaded with many different types of information. employs a seemingly arbitrary color scale, and research has shown that the cone element itself leads to misinterpretation. For example, some people feel safer in locations just outside the cone, with some even believing that there's no imminent risk beyond the cone at all. Related evidence suggests that people believe that areas along the central black line are in greater danger. Moreover, the shape of the cone is often misinterpreted to communicate information about the size and intensity of the storm. In this study, we explored how design elements influence interpretations of hurricane risk by comparing non-expert responses to the NHC cone of uncertainty against two new forecast graphic prototypes. We followed a user-centered design process. To understand readers and their context of use, we first conducted focus groups. We asked questions about sources of hurricane information, responses to hurricane threats, and interpretations of hurricane forecast and warning information. Participants were shown both the 3-day and 5-day cones of uncertainty. In the next phase, we produced 3 design prototypes using data from historical hurricanes overlaid over a map of the United States. To evaluate our designs, we conducted interviews. During the interviews, participants were shown the 3 visualization prototypes. We asked participants questions about each of the visualizations. Participants were also asked to rank the visualization prototypes in order of preference. The first design used was the existing COU with only minor updates. For example, we increased color contrast, highlighting the cone over the ocean and landmass. The second design, our redesign A, blurred the boundaries of the cone and employed a uniform gray shading. In addition, we added explanation above the map that expands on the label of what the original NHC cone of uncertainty contains. Colors for watches and warnings were also changed to a sequential color palette ranging from light yellow for tropical storm watches to dark red for hurricane warnings. We also added contextual explanations of map abbreviations such as M for major hurricane. The third design, our redesign B, employed different gradations of the gray shading. Regions closest to the official NHC forecast position were shaded darker, and regions further were lighter. We also used separate maps for watches and warnings and the cone, while also maintaining the changes in the legend and color schemes of redesign A, but expanding the how to read the map legend. The NHC design received the most first place votes. Analysis with Friedman test, however, showed no significant effect of design on preference. Of those picking the NHC first, 58% picked redesign A as their second choice, showing a pattern of favoring designs that more closely align with the NHC. Our interviews revealed some of the factors that influence participants' graphic preferences. Cone design was a primary reason for top choice selection across the 3 graphics. Other factors included treatment for watches and warnings, familiarity, color scale, legend, and visual design. Most participants preferred the NHC graphic and indicated that their preference was because of the cone design, specifically that the NHC cone had a greater visual saliency and drew their attention to what they perceived to be the most important or the focal point of the graphic. However, when describing what the NHC cone conveys, of the participants that provided interpretations, all that did provided erroneous interpretations, such as indicating that the black border bounds the impact of the storm, contains all possible storm paths, and offers certainty about where the storm begins and ends. Although the cone design was the top reason for participants' first choice of the NHC graphic, to a lesser extent, the cone design was also important for those who selected redesign A and B. For the alternative designs, participants' responses included both correct and incorrect interpretations. The incorrect interpretations of the shaded cone used in redesign A and B included that the fuzzy boundary implies that the warning is less urgent and indicates that the further you are from the center of the cone, the less likely you to feel the storm effects. Correct interpretations noted that the shading depicts probability that the storm can pass outside of the cone. For redesign B in particular, a few participants indicated that the shaded cone with the gradient did a better job conveying this uncertainty in the forecast and eliminated a false sense of security. Participants that selected the NHC graphic as their first choice indicated that familiarity with the graphic played an important role. However, the perceived cognitive ease in processing familiar representations of information did not alleviate, as we explained previously, misinterpretations due to the cone of uncertainty design. Shown here are some representative voices. Our focus group findings suggested that watch and warning map overlay contributed to information overload. Because of this, with redesign B, we separated watch and warning information from the cone. Of the participants who selected redesign B as their most preferred, many explained that presenting the watches and warnings separately influenced their preference. For some, the separation of information better highlighted coastal areas under threat. However, many more participants indicated that overlaying the watches and warnings was critical in storm path estimation, suggesting that underlying the forecast was dependent upon watch and warning information. In our focus group, a common complaint was that the NHC COU is extremely cluttered, as it contains several layers of information that often interfere with each other. So we deconstructed the graphic and created a multi-section layout for redesign B. The layout for redesign B, unfortunately, was a dissatisfier for many participants. In particular, many participants indicated that redesign B had higher visual search demands because the layout lacked hierarchy, not guiding the eye to design elements based on their relative importance. Participants felt that the layout was unclear, with design elements sequenced without apparent reason, making the message difficult to discern. Many also noted that there were twice as many design elements to process, increasing the complexity of the visual representation of information. To get a better sense of information dependencies for non-experts, we will continue to explore a mental models approach to better understand the reader's needs. Participants appreciated the NHC's distinct color scale because it allowed for easy identification of tropical cyclone type and alert level. For redesign A, not so much. The color scale just didn't offer sufficient discrimination. But this wasn't much of a problem for redesign B because we had different maps to convey alert levels. With this work, we had mixed results, and therefore we cannot confirm that the alternative designs were more effective. The study, however, provided promising hints directing our future efforts to improve hurricane forecast graphics. And finally, based on our findings across research activities, our future design efforts will be in designing products that emphasize hazards and risk rather than just the possible path of the storm center. Special thanks to Yuling for funding this. Thank you. Any questions?
Thank you. Excellent. So we have a few questions, and what we're going to do here, I think, is do a short Q&A for this paper, and then we'll have another larger discussion again for a few minutes, and then we'll have a little closing for this workshop. So one question here from Les Padilla is that she's asking, there's this work by Roginski et al. From 2017 that tested a cone with blurry boundaries. Mm-hmm. Have you compared your work with theirs, or do you have a sense of how it would compare?
Hi, Lace. I'm a fan of your work, so thanks for asking the question. We were inspired by that study. You were also one of the co-authors from that study, and that one, if my recollection is correct, so bear with me if it's not, it was an experimental assessment in lab, and it was focused on estimates of property damage or damage. I think it was damage overall. What we did was a little different. We did do a lab-based experiment, and we followed more of the Cox et al. Model, where we were looking at estimations of probable path within the 3-day cone. So from the current position to the boundary of the 3-day cone. We're in the middle of analyzing our data. So I can't tell you in terms of the performance metrics or the more objective metrics, what we found. What we did see from our preliminary analysis that we didn't see much of a we didn't see much of a difference in improvement in terms of interpretation of based on the different graphics. We also did eye tracking. That one was very interesting because we saw the importance of watch and warning information and overlaid on the cone of uncertainty in estimating probable path.
Great. So, and there's another question here from Chuck, which is a question that I was also wondering about, which is, sorry, did you get any chance to talk to the folks at NHC that are, I'm sorry, did you get a chance to talk to the folks at NHC that are involved in the current designs? Like, do you know what their feelings are, what their thoughts are on their own design and all these alternative designs that people have been proposing, and whether they might change their approaches?
Yeah, NHC is a stakeholder for our project, so we talk to them often. We presented these graphics to them before we started running the experiments, and we got their feedback, and we made changes that may facilitate possible operationalization of these graphics if they were to implement them. But they were waiting to see what our results were before they consider whether or not it should be a part of their representation, their graphic set. However, it is a general trend that in terms of communicating probabilistic risk for weather hazards, that they're moving more into threats and impacts rather than forecasts for communicating with the public.
Great. Okay. So then, well, I suggest we move on to sort of the broad discussion for a few minutes. We're running a little bit behind, but I think we should have at least a few minutes here to chat, and then we'll close the workshop for today. So thank you all speakers for the whole day, but especially for this session. Of course, I really appreciate all the work everybody put into this, both the papers and your presentations, especially in this weird way we're doing this right now. So I really appreciate that. And I'm happy to open the floor to folks' ideas, thoughts, questions. Anybody want to be the first?
Barbara, thanks so much for your paper. I thought it was very, very interesting. And I have a number of questions, but I'll start with, as a user of the cone graphic, I think one of the things that is missing for me is understanding the size of the storm, because it just shows you where the center is. It doesn't show you how big the storm is, for instance, when it would make landfall. Have you looked at any iterations that actually show maybe like circles of the size of the storm and how much space it covers?
Just to talk about this particular study, we thought that moving to this gray shading might kind of alleviate that impression. But some of the comments that we did hear is that it actually looked more like the storm than the bounded cone because of the color and the fact that it was blurry towards the boundary. So in going forward, we are moving away from representing the cone and moving more towards threats and impacts. So we're not moving forward with trying to eliminate that problem.
Okay, so so do we know? So I would suspect that the cone is used. Okay, I'll just put it this way: how is the cone primarily used? And what I'm thinking is, do individuals read the cone, or are they seeing it on their local news broadcast, for example?
We in part of our focus groups, we also ran a pretty large-scale survey across Florida residents, and we've mostly been sticking with Florida as our population of investigation. But we have found that the most important or the most trusted source of information is television, as well as mobile apps. That's what we're seeing. So they're essentially, what we've seen from the people that we've been talking to is that they want the information to be explained to them. So mostly the general public or the people that we've been talking to have been relying on a mediator to communicate the message, but they have the visuals and they're being talked to about the visuals.
Right.
Yeah, so Ben just said something on Discord about familiarity being one of the topics today or the themes today, and I think that that's a very good point. There is a lot to be said, I think, about how it's hard, I think, and I think we actually saw this in some of the papers today, it's hard for people to deal with things that they're just not familiar with, even if they sort of objectively are better. And I think most of the experts agree that it's a better idea. But if you're only used to seeing it the other way or some other way, it takes so much longer to wrap your head around it. So I really wonder what we could do about that, because that seems like a real big obstacle and makes it really harder to get all this good work out.
Well, I wonder if that's just part of the evolution of the field, right? I think we all remember there was that Pew survey several years ago that found like 60% of people could accurately describe how to read a scatter plot, which you could either say that that's a lot or not enough, depending on your perspective. But I would bet that if you asked average New York Times readers 10 years ago to read a scatter plot, it would be some X%. And if you asked the same people today, it would be much higher, right? Because it's the evolution of how they've been publishing their work. So I wonder if there's, and Robert, you've done a lot of work on this. I wonder if there's more, what there should be is more of a intersection between the academic community and the practitioners, right? So that the practitioners can learn how to better educate their standard audiences and how to read these other graphs or techniques.
This is something I've been thinking about a lot in the last few years. Oh, I'm sorry. Go ahead. Go ahead, Robert. I've been thinking a lot about how, because I work a lot with populations that have lower levels of literacy and trying to meet their needs specifically. And you know, if you've got a population, say people who have diabetes and have to do a lot of intensive self-management, you have their captive audience because they're going to have to continue to interact with their data over the long term, and people can learn. So even if they don't start out understanding a line graph, you can teach them. And so I'm really interested in how do we scaffold that information in a way that makes it very accessible and brings people along in that evolution that you described.
I think it's also a question, of course, who are the people who can do that? And so news graphics, since you mentioned New York Times, of course, I think news graphics with their annotations, which aren't really a thing we do a lot in the visualization sort of field, but those I think can introduce people a lot into what they're seeing, and that's another way of sort of getting people more familiar with things that they're not familiar with yet. So that may be another way.
Yeah, my thought is just that different visualizations have different degrees of ease of use or ease of understanding, whatever we want to call that. And we should use them where they're most likely to succeed. But I think over time, the more complex ones, the more difficult ones, we'll probably find a broader audience if we just gradually expand them from an audience that is motivated and able to a broader audience. The challenge is right now, I think we have a pretty good idea, but one of the challenges is figuring out where all these different types of visuals and charts fall in that range.
All right, so I'm going to, we're running about 5 minutes behind now. So I'm going to just sort of like close a little bit, and then we can keep our discussion going here. But I think we'll end the actual workshop basically now in the next few minutes. So I just wanted to say, first of all, thanks everybody who has submitted papers and who has presented through the day or through this half day, whatever it was, several hours. So I really appreciate that. I also want to thank our student volunteers. There's Daria, who has been running our videos and everything here in our own little Zoom call. And then there's also Noel and Kiki, who have been on Discord. So I just wanted to thank you guys. And then finally, so this is the third time, as we mentioned in the intro, this is the third time Ben and I have been doing this. And so we are now sort of the old men of VisComm, and we're going to roll off and hand things over to the next generation of visual communicators, that being Adriana and Alvitta. And they are looking for co-chairs. So if you are interested in doing that, you should chat with them. Also, one final reminder, there is the VisComm.io page that you should go to for all the papers that you saw today. So all of them are linked from there. And there's also a link to the Google group there now. And I think there should be a link to our meetup that is happening on Thursday. So make sure to check that out. And I don't know if Ben wants to say anything, any last words as the and not the other outgoing chair, but other than that, we're going to hand things over now to Adriana and Alvitta.
Just a thanks to everybody who was involved this year and in the previous 2 years as well. It's been a great ride.
I hope everyone can make it to the meetup. I'll see you on Thursday and we can chat more informally. I'm looking forward to it.
Me too.
Thank you all.
Morse complexes have shown a great utility in understanding the topology of complex scientific datasets. The noise in the scalar field, however, can significantly distort the Morse complex topology. Hence, we study the extraction of Morse complexes for ensembles of noisy scalar fields through their uncertainty visualization using our proposed statistical summary maps.
We present a flexible and easy-to-use software infrastructure for interactive rendering of large-scale display walls, either from on-site or from remote cluster. The display servers can easily be configured to support a range of typical network and display hardware configurations. The client library provides a straightforward interface for easy integration into CPU and GPU renderers. We also demonstrate this framework for use in deploying low-cost alternatives for display walls.
CarxS is an authoring system which enables rapid creation of zooming-based scatter plot-like visualizations in just tens of lines of JSON. We contribute a declarative grammar for such visualizations, which captures a large design space. By working with multi-node database spatial indexes, CarxS enables interactive browsing of billions of data points. Come listen to our talk to learn more.
Taylor-Coelho flows is a turbulent fluid motion created in the gap between the two rotating cylinders. The traditional reason-based methods are only able to capture the small-scale coherent structure. The detection of the large structure depends on the 2D cross-section, which is not the true configuration. We adapt the feature-level set methods and the density estimation to combine multiple attributes and use them as the filter to separate large and small-scale structure.
Deep learning models have become ubiquitous, but we often lack interpretations for their decisions. We developed a visual analytics system to interpret models that perform multi-class DGA classification. For each layer of the model, we visualize clusters inside its activation data, showing how classes and clusters relate to each other. In addition, we provide a decision tree to explain how these clusters are constructed.
Progressive visual analytics provides intermediate lizards in the middle of computation to address a long computational delay. However, such intermediate lizards are uncertain, so findings from these lizards can turn out to be incorrect for the entire data. In progressive visual analytics with safeguards, we suggest to risk the uncertainty, but we allow humans to leave safeguards every time they risk the uncertainty.
We present an algorithm for raycasting Hermite spline tubes, which result from letting a sphere trace Hermite splines that define its visual attributes. Since we do not employ tessellation, our method enables smooth curves and transitions of radius and color along the tube. Join us for an in-depth look at the intersection routine that enables raycasting hundreds of thousands of them efficiently in real time, and see what makes them a powerful new tool in the inventory of curve and line data visualization.
Ray tracing techniques can create images of astonishing realism and beauty. In the last years, the performance of those techniques has been increased significantly using dedicated hardware. Who thought that it's also possible to accelerate this? We show how to dramatically accelerate force-directed graph drawing with RT cores, yielding a speed up of 4 to 13x. If you want to know more, please see our talk.
CMed is a visual analytics framework for exploring medical image data annotations acquired from crowdsourcing. CMed can be used to visualize, classify, and filter crowdsourced clinical data based on a number of different metrics such as detection rate, logged events, and clustering of the annotations. CMed provides several interactive linked visualization components to analyze the crowd annotation results for a particular video and the associated workers.
As commonly known, dimensionality reduction techniques and their interpretations are complex, biased, and uncertain. In drug design, this highly complicates the search for similar and new chemical compounds. To overcome this issue, Canva brings comparison of different molecular descriptors and properties into one tool, featuring planar, 3D, and table views for evaluating the trustworthiness of high-dimensional data projection.